The morning light on a tropical reef does not arrive gently. It pours downward in broken ribbons, scattered by drifting plankton and suspended sand, turning the shallow sea floor into a shifting mosaic of gold and blue. On this patch of reef, the water is shallow enough that every passing cloud casts a slow, rolling shadow over the landscape of corals, sponges, and anemones. The currents move like long, steady breaths, pushing and pulling the reef's inhabitants in a hypnotic rhythm. Somewhere within this vibrant city, where danger hides behind beauty and survival depends on precision, a cluster of orange and white palm-sized bodies hovers above a crown of tentacles. This is the domain of a clownfish family, and the structure beneath them is their fortress. A living, toxic house whose walls kill almost everything except its tenants. To the casual eye, the anemone appears delicate, its tentacles swaying like soft ribbons in a breeze. Yet each tentacle is armed with microscopic harpoons that fire on contact, injecting venom potent enough to stun or kill small fish. This venom is governed by nematocysts, stinging organelles that evolved long before vertebrates ever existed. To brush against these tentacles without protection is to be burned, paralyzed, and consumed. But the clownfish glide among them with the certainty of creatures walking through their own front door, brushing gently against the tentacles as if greeting a familiar doormat. The reef may look chaotic, yet this house is as orderly as any kingdom. And like any kingdom, it has laws, obligations, and an unspoken contract that decides who lives here and who dies trying. This alliance between clownfish and sea anemone is ancient, a partnership carved by millennia of selective pressure. The clownfish cannot survive without shelter, and the anemone cannot move from its anchored position. One offers offense, the other defense. One offers venom, the other vigilance. The arrangement is so perfect that ecologists often describe it as a rental contract. The anemone provides the home, the clownfish pays the rent. Except the currency is not food or territory. The currency is service. A clownfish survives in the anemone only because it has evolved a specialized mucus layer coating its skin. Unlike the skin of most fish, this mucus lacks the chemical triggers that activate the anemone's stinging cells. When a clownfish first approaches its host, it does not dive in immediately. It performs a careful dance, brushing its body against the tentacles in short bursts, allowing the anemone to sample and acclimate to the fish's chemical fingerprint. Gradually, the clownfish coats itself in a thin mixture of its own mucus and that of the anemone, creating a biochemical disguise. Once accepted, the tentacles no longer fire on contact. The fish becomes invisible to the anemone's weaponry, a tenant approved to enter without consequence. Once inside, the clownfish begins paying its dues. Butterfly fish patrol the edges of the reef, gliding with delicate precision as they search for tentacles to nip. They are among the few fish capable of plucking apart anemone tissues without being stung, and their presence spells slow death for a stationary anemone. But clownfish are territorial to an extreme. They charge at butterfly fish several times their size, chasing them from the perimeter with bursts of speed that seem impossible for such small bodies. In this world, bravery is not optional. It is necessary, rent. The clownfish also fertilize their home with nitrogen-rich waste, a constant nutrient supply that boosts the metabolism of the anemone's symbiotic algae. Because anemones, much like corals, host photosynthetic partners, they rely heavily on sunlight and nutrient exchange to fuel their growth. A well-fed anemone grows faster, repairs damage quickly, and maintains healthy tentacles, all thanks to the steady nutrient flow from its clownfish tenants. But the rent goes deeper. The clownfish also fan the tentacles with their fins, circulating oxygenated water around the anemone's surface. This behavior reduces the accumulation of sediment, increases gas exchange, and flushes away parasites or debris that might settle between the tentacles. In a reef where currents can stagnate during certain tides, the clownfish's constant fanning acts like a ventilation system, keeping the host clean and aerated. Researchers observing these interactions often remark that the clownfish display a degree of caretaking that borders on compulsive. They tend their home as though it were alive, because it is. Their survival is tethered to its survival, and the contract binds them as securely as any written law. For juvenile clownfish, the anemone is not merely a shelter, but a labyrinth. A young clownfish spends its earliest days learning the layout of its host structure. Each tentacle cluster becomes a familiar alley. Each opening between the folds becomes a mapped escape route. The fish memorize where they can safely retreat, where danger tends to strike from, and where siblings usually hide. Their movements are not random. Over time, juveniles perform intricate tours through the tentacles, testing currents, sensing chemical gradients, and rehearsing routes they might need during a predator attack. Scientists have documented that juveniles show spatial learning capabilities uncommon for such small fish. They navigate their anemone home with the confidence of animals that understand its contours by memory, not instinct alone. Hierarchy within the anemone is rigid. The largest female lives at the center of the tentacle crown, controlling breeding rights. The next largest male holds second status. All other individuals remain non-breeding. Should the dominant female die, the dominant male undergoes a complete sex change, becoming the new female. The next largest juvenile then transitions into the breeding male. This dynamic ensures stability within the contract. The anemone always has a caretaker group ready to defend it, no matter which individual rises to power. Here, size is destiny, and destiny shapes the rental agreement itself. But the contract is fragile. When ocean waters warm beyond the narrow threshold that anemones can tolerate, their symbiotic algae, the microscopic organisms that provide them with energy through photosynthesis, begin to die or flee. Without these algae, the anemone loses its pigments and turns ghostly white. This phenomenon is bleaching, and it is not merely a shift in color. It is the unraveling of the anemone's internal machinery. A bleached anemone becomes weak, its tentacles shrinking, its metabolism slowing, its venom production dropping. For the clownfish, this is the equivalent of watching the walls of their fortress begin to crumble. The once lethal tentacles become ineffective. Predators that previously avoided the anemone's reach now risk closer approaches, sensing that the sting is no longer so potent. The clownfish do not abandon their home immediately. They often remain loyal long past the anemone's functional decline, continuing to aerate the tentacles, feed the algae that no longer respond, and chase away predators with the same determined energy. But loyalty cannot reverse biology. If the anemone remains bleached for too long, it starves. It withers. Eventually, the clownfish must leave or die alongside their collapsing home. And when they leave, they enter a reef where unclaimed anemones are rare. Competition is brutal, and predators are eager to catch homeless fish. A homeless clownfish is a vulnerable one. Without the chemical shield of its anemone-coated mucus, the fish loses much of its protection. Even if it finds a new host, it must perform the initiation dance again. The slow, delicate process of acclimating to the new anemone's tentacles. But the new host may already have tenants. Anemones tolerate only one breeding pair and a small hierarchy of subordinates. Any outsider faces swift rejection or lethal aggression. What seems like a simple relocation becomes a high-stakes gamble with survival. Bleaching is not the only threat to the rental contract. Physical disturbances, sedimentation, storms, and pollution can shift or injure anemones. If the anemone detaches from its substrate, it drifts helplessly, its tentacles unable to anchor and its body exposed. Clownfish rarely follow a drifting anemone. They require stable territory to maintain their hierarchy and defend their boundaries. In such cases, the contract collapses instantly. The home is gone, and the tenants scatter. The clownfish-anemone partnership reveals an ecological truth often overlooked by casual observers. Even the most iconic symbioses are fragile, conditional, and dependent on narrow environmental windows. The clownfish does not live with the anemone because of blind trust or innate compatibility. It lives there because evolution sculpted a perfect exchange of services. The fish defends, cleans, fertilizes, and ventilates. The anemone shelters, protects, and amplifies the fish's territorial advantage. Both gain, but both depend. Remove one partner, and the other falters. In the broader context of reef ecology, This arrangement contributes to the diversity and resilience of the ecosystem. Anemones with clownfish tend to be healthier, larger, and more capable of reproduction. These robust anemones create microhabitats that host small crustaceans, worms, and algae. The clownfish themselves attract plankton and detritus through their constant movement, feeding tiny organisms that hide among the tentacles. The rental contract, therefore, ripples outward into the reef's greater economy. What begins as a simple exchange between two species becomes a cornerstone of a small community. Yet the greatest insight lies in the details of how the clownfish behaves when the contract is threatened. A clownfish is vigilant, attentive, and deeply entwined with the well-being of its host. Its fins fan tirelessly. Its eyes scan endlessly. Its movements are calibrated to maintain the delicate chemistry of the home. When bleaching strikes, the clownfish become almost frantic in their caretaking, as if trying to revive a partner slipping away. These moments reveal that intelligence in the reef is not always measured by tool use or innovation. Sometimes it is measured by how instinct and environment intertwine, creating behaviors that look like devotion, but are rooted in survival. In the end, the clownfish's life is defined by the walls of its toxic house. It is a creature that thrives because it has adapted to danger rather than avoided it, turning venom into shelter and risk into opportunity. The rental contract it maintains with the anemone is one of nature's most elegant negotiations. A living house with an armed perimeter, defended by tenants who pay their dues with vigilance, nutrients, and unwavering loyalty. And as long as the reef remains stable, this contract continues, a tiny but indestructible agreement in a sea where survival is never guaranteed. At first light, the reef wakes with a slow shimmer, as if the entire underwater landscape stretches itself awake beneath the rising sun. The sea anemone sits anchored to its patch of rock, unblinking and unmovable, a creature whose life unfolds across years rather than moments. The morning currents thread through its forest of tentacles, carrying nutrients, stray plankton, and the faint chemical signatures of every organism that passes. To the casual observer, the anemone appears passive, a simple ornamental fixture in a complex environment. But beneath this illusion of stillness lies one of the reef's most selective gatekeepers, a landlord whose weaponized walls allow entry only to tenants that meet very specific biochemical criteria. Everything else is turned away at the door, often fatally. The anemone's tentacles sway in the soft rush of the tide, each one lined with thousands of nematocysts, microscopic capsules wound tight like spring-loaded darts. These structures represent one of the earliest animal weapons on Earth, developed long before bones or brains became common. When a foreign body brushes against the tentacle, chemical receptors help determine whether it is friend, foe, or food. A misidentified intruder is stabbed instantly, paralyzed, and drawn toward the central mouth. For countless reef creatures, a single accidental touch means death. Yet within this lethal fringe, a few chosen tenants move freely, slipping between tentacles with the confidence of residents who know they belong. Their acceptance is no accident. It is the result of a layered recognition system that functions like a biological background check. Each clownfish species has evolved a mucus shield that mimics or neutralizes the anemone's sting response. When a clownfish begins its tenancy, it introduces its chemical fingerprint slowly, brushing its body against tentacles in controlled intervals. This process is not simply acclimation, but a negotiation. The anemone's receptors gradually learn that this foreign body does not trigger the firing impulse. The fish becomes chemically invisible, but the anemone decides whom it tolerates. Some anemone species host only one clownfish species. Others allow multiple. The specificity varies wildly across the Indo-Pacific, forming a mosaic of miniature real estate markets scattered across coral systems. These patterns reveal a striking truth about reef evolution. Symbioses are not generic partnerships, but highly tuned matches shaped by geography, competition, and environmental pressures. Consider the magnificent sea anemone, a species whose large size and broad tentacles make it one of the most desirable homes for clownfish. It accepts a select group of fish tenants, usually those with robust mucus compositions capable of passing its stringent chemical defenses. On the other hand, The adhesive sea anemone tolerates only a narrow subset of tenants. Even closely related fish species fail its recognition test. These subtle differences create invisible boundaries on the reef, where some clownfish travel long distances searching for a suitable host, and others remain locked to their birthplace, restricted by the availability of compatible landlords. But clownfish are not the only residents in this apartment block ecosystem. Between the tentacles, hidden from the glare of passing predators, live small shrimps of the genera Periclymenes and Thor. Their bodies glisten with transparency, rendering them nearly invisible except for faint patterns or color streaks. These shrimps also rely on chemical mimicry to avoid being stung. Their mucus, like that of clownfish, carries surface compounds that deactivate nematocysts on contact. Unlike fish tenants, however, shrimps play a more subtle role in the ecosystem. Some act as cleaners, picking parasites or debris from the anemone's body, while others feed on mucus or cope pods that drift into the tentacle forest. Their presence creates a secondary tier of occupancy, tiny renters occupying hidden alcoves within the larger home. Crabs too join this micro-community. The enigmatic anemone crab, flattened and patterned for camouflage, scuttles gently across the base of its host. It opens feathery appendages to filter feed, taking advantage of the water flow generated by the anemone's position and the constant movement of clownfish. The crab does not challenge the anemone's authority. Instead, it lives quietly on the periphery, behaving like a respectful subtenant who avoids conflicts by staying near the shared walls, rather than venturing into the landlord's central chambers where stings are more frequent. The crab's armor allows it to endure occasional accidental brushes, but it maintains distance with careful, measured steps, demonstrating an instinctive understanding of the rules of its environment. All these tenants, fish, shrimps, crabs, rely on biochemical compatibility to stay alive within the anemone's deadly perimeter. The anemone, in turn, benefits from an increased flow of nutrients, cleaning services, defense against predators, and the circulation of oxygenated water. Yet it is the anemone itself that controls the distribution of these benefits. By accepting certain tenants and excluding others, it shapes the population dynamics of the reef around it. On patches of coral where anemones thrive, fish diversity tends to increase. In part, this is because their intimidating tentacle boundaries offer safe zones for juveniles of many species. A hunting predator, whether a wrasser, moray eel, or grouper, tends to avoid the reach of an active anemone. Even predators that could withstand the sting prefer to hunt elsewhere, knowing that the risk of being stunned in the chaos of a chase is not worth the energy gained from a single kill. This effect extends outward. Areas with multiple anemones often develop into biological hotspots. Small damselfish dart around the bases, using the anemone's presence as a buffer zone against territorial competitors. Plankton-eating species form small schools nearby, drawn by the swirling currents that clownfish generate as they fan their hosts. Even corals benefit indirectly. Fecal matter from residents enriches the surrounding substrate with nitrogen and phosphorus, enhancing microalgal productivity and fueling the growth of nearby polyps. The sea anemone, rooted and motionless, acts as a catalyst for movement and life around it. It is not a passive organism, but a landlord whose decision to host tenants radiates ecological consequences far beyond its tentacle tips. Being a landlord in the reef, however, comes with risks. Predators that specialize in consuming anemones, such as certain butterfly fish, patrol the landscape with practiced efficiency. Their narrow snouts and scalpel-like jaws are adapted specifically for plucking tentacles without triggering full envenomation. In these encounters, the clownfish often become the anemone's hired security, chasing the butterfly fish with surprising aggression. But the anemone itself also responds. When threatened, it retracts its tentacles into its base, forming a tight ball that protects its more vulnerable internal structures. This retraction is metabolically expensive. It disrupts feeding, reduces photosynthesis from symbiotic algae, and halts gas exchange across the tentacle surfaces. The anemone does not retract lightly, and it relies heavily on its tenants to minimize the need. Water quality also tests the landlord's resilience. Sediment deposited by storms or dredging activities can clog its tentacles, forcing the anemone to extrude mucus in large sheets to rid itself of debris. These mucus veils drift away in the current, pulling worms, detritus, and parasites from the anemone's surface. But prolonged sedimentation weakens the anemone by starving its symbiotic algae of sunlight. When stress accumulates, the anemone may bleach, expelling its algae and turning stark white. While this state is reversible, long periods of bleaching can lead to tissue loss or death. A bleached anemone is far less likely to accept new tenants and may even reject or expel existing ones, temporarily losing its position as a vibrant hub of activity. Despite these challenges, the sea anemone remains one of the most influential architects of microhabitats on the reef. Its ability to decide who lives within its boundaries creates pockets of stability in environments where shelter is scarce and competition is unforgiving. A young fish looking for protection will often approach an anemone cautiously, its life hanging on the thin line between acceptance and fatal sting. Many species attempt residency and fail. Their mucus composition, swimming patterns, or chemical signals do not meet the landlord's criteria. Only species with the correct evolutionary history, those whose ancestors forged symbioses across generations, can pass the gate. This selective tenancy becomes especially meaningful when viewed on a landscape scale. Reefs are patchworks of opportunity, where some areas teem with life and others remain barren stretches of rock. Sea anemones act as magnets in this mosaic. Where they take root, food webs condense. Energy circulates more efficiently. Predation risk drops for vulnerable species, creating a safe nursery zone within a dangerous environment. Even after the anemone dies, the surrounding community may persist for a short time, maintaining structure until erosion or competition reshapes the space. At the molecular level, the anemone's landlord role is even more remarkable. Its stinging cells operate based not only on mechanical triggers, but also on layers of chemical recognition. These chemical gradients determine whether the nematocysts fire, and they can vary across tentacles depending on age, light exposure, and recent feeding events. This means the anemone can modulate its defense within its own body, potentially responding differently to a known tenant versus a persistent parasite. Although the anemone lacks a centralized nervous system, networks of nerve cells allow it to coordinate contraction, expansion, feeding, and stinging responses in surprisingly adaptive ways. Its decisions may be simple in comparison to vertebrates, but they are nonetheless decisions, and they shape the distribution of life around it. In this sense, the sea anemone embodies the essence of sessile power. It does not chase prey or flee predators. It does not travel across reefs in search of territory. Instead, it builds an empire precisely where it stands, inviting selected species to share in its poison-tipped sovereignty. These tenants, in turn, elevate the landlord's influence. Each clownfish patrol, each shrimp cleaning sweep, each crab filter feeding session contributes to the maintenance of this living stronghold. The anemone is the immovable anchor. Its tenants are the dynamic engines that keep the system alive. From above, a diver might see only a patch of waving tentacles, but from the perspective of the reef's smaller inhabitants, the sea anemone is a towering landlord with strict rules, powerful defenses, and a critical role in maintaining local biodiversity. Around it, life gathers. Near it, predators hesitate. Within it, a miniature society of tenants thrives under the protection of its toxic curtain, and through its presence, entire coral patches transform from barren stone into vibrant neighborhoods, each one pulsing with the complex interplay of chemistry, behavior, and biology that defines the reef. In the dim corridors of the coral labyrinth, where sunlight filters through cracks like fractured gold, and shadows drift as slowly as the tide itself, lies one of the reef's most enigmatic hunters. The moray eel does not patrol like a reef shark, nor does it glide with the elegance of a ray. It waits. Its body, long and muscular like a coiled rope, lies tucked within a crevice, its head protruding just far enough for its jaws to taste the current. The eel's mouth opens and closes rhythmically, not in threat, but in necessity. Morays breathe by pumping water through their gills, and the constant opening of their jaws creates the illusion of a perpetual snarl. In this stillness, in this near-complete concealment, the moray eel becomes an animal defined by patience. Around midday, when currents shift and small fish begin to forage among branching corals, another shadow approaches, broader, heavier, and moving with deliberate purpose. A grouper, thick-bodied and powerful, hovers above the reef. Its large eyes scan the topography, searching for something the eel cannot see, prey lingering in open water or fleeing across the sandy gaps between coral heads. When grouper and moray share territory, a remarkable transformation unfolds. Two predators, each with different strengths and limitations, synchronize their abilities into a single, coordinated attack system that leaves prey with no possible escape route. The grouper begins the interaction with a head-shaking gesture, a distinctive invitation signal directed toward the hidden moray. Unlike most interspecies encounters on the reef, where predators avoid or ignore each other, this signal is persistent. The grouper hovers near the crevice entrance, shaking its head in short, sharp bursts, as though urging the eel to awaken from its stony fortress. The moray recognizes this gesture through a combination of visual cue and the subtle pressure waves produced by the grouper's movement. After a moment, the eel emerges, its body unfurling from the crevice like a banner of living muscle. Once the moray exits its shelter, the two hunters form a loosely coordinated partnership. The grouper takes position slightly ahead, scanning wide spaces and ready to sprint. The moray slips into the labyrinth, weaving through narrow passageways inaccessible to large-bodied predators. This cooperation forms a deadly net around any prey in the area. Small fish, normally able to evade one predator by retreating to either tight shelters or open water, find themselves trapped in a web of intelligence and muscle that adapts to their movements with uncanny precision. This partnership is not symbolic or accidental. It is one of the most well-documented examples of interspecies cooperative hunting in marine ecosystems. From a scientific perspective, the partnership between morays and groupers is striking because of its cognitive implications. Experiments conducted in controlled coral environments demonstrate that groupers will choose to recruit a moray when prey hide in structures. Presented with an option to hunt alone or summon the eel, the grouper selects the eel when the hunt requires probing into tight spaces. In other trials, when prey remain in open water, groupers do not signal the eel, relying instead on their own speed and ambush capacity. This selective partnership reveals decision-making rather than reflex. In the wild, this alliance amplifies the moray eel's natural hunting style. A moray's flexible, ribbon-like body allows it to maneuver into crevices where prey seek refuge. While many predators attempt to reach into holes with limited success, the moray's entire body is designed for this task. It moves with deliberate, almost serpentine precision, using an undulating motion driven by longitudinal muscles running along its length. These muscles contract in waves, pushing the eel forward even in the tightest channels. Inside the crevice, the moray's presence alone flushes prey outward, and this is where the grouper becomes essential. The moment a small fish bolts into open water, the grouper launches forward with explosive acceleration, cutting off escape with a single decisive strike. Neither predator alone could trap prey in such a flawless pincer movement. Together they turn the coral maze into a closed arena. Yet the most extraordinary adaptation the moray brings to this partnership lies not in its body shape, but in its jaws, or more accurately, in its second set of jaws, hidden deep within the throat. The moray eel possesses pharyngeal jaws, a rare and powerful adaptation in which a second pair of jaw bones, equipped with sharp teeth, shoots forward to seize prey after the primary jaws clamp down. In most fish, pharyngeal jaws remain fixed in the throat, used for grinding or crushing food. In morays, they are mobile, reaching forward to grip prey and pull it backward. This mechanism compensates for the eel's narrow skull and limited suction ability, allowing it to capture and swallow prey in confined spaces where suction feeding would fail. When the moray strikes inside a crevice, the pharyngeal jaws make the attack nearly inescapable. They function like a biological grappling hook, securing prey even if the eel cannot fully open its mouth in the cramped environment. In cooperative hunts, these double jaws serve as tools that complement the grouper's speed and power. While the grouper chases in open water and relies on sheer force to engulf prey, The moray's double jaw system ensures that hiding prey cannot wedge themselves into inaccessible cracks. Between the eel's reach inside the crevices and the grouper's command of open areas, prey become trapped within overlapping zones of predation, where every escape route is sealed. As evening approaches and the ambient light fades, the dynamics shift again. Moray eels, primarily nocturnal hunters, grow more active, while groupers continue to patrol crests and channels. Their cooperation intensifies during low light hours, when prey behavior becomes more erratic. At dusk, many reef fish enter transitional states, moving between daytime foraging areas and nighttime shelters. Some species hover just above the coral surface, trying to determine when it is safe to retreat. Others dart through crevices, hoping to escape both diurnal predators and nocturnal ones. This shift in behavior plays directly into the hunting strategy of the moray grouper partnership. The grouper intercepts prey that hesitate in open areas, while the moray advances through the structure with renewed aggression, using its sense of smell and lateraline sensitivity to detect faint vibrations of panicked fish. These combined sensory systems represent another layer of complementarity. While groupers rely heavily on vision, the moray eel's eyes are adapted more for low light and depth perception than for color discrimination or long-range clarity. The eel's true sensory strength lies in its chemoreception, the ability to detect chemical cues in the water column. This allows it to sense injured or stressed prey inside hidden pockets of the reef long before other predators become aware. In cooperative hunts, the moray becomes not only the invader of hiding spaces, but the tracker that follows, scent trails through complex networks of channels. For the grouper, this sensory complement fills a critical gap. Although strong and fast, the grouper is limited by its bulk. It cannot maneuver through the tangled lattice of branching corals or worm its way into rubble piles. But with the eel entering these spaces, the grouper becomes an aerial predator hovering above a three-dimensional hunting field. When prey flee past the eel and burst into open water, the grouper's powerful tail launches it forward in a straight, unstoppable vector. The combination of moray ambush and grouper sprint forms an attack sequence that bridges environments, enclosed interior spaces, and exposed water columns. Researchers observing this behavior in natural and experimental settings discovered that cooperation between eels and groupers is not passive, but reciprocal. In some documented cases, morays respond to groupers' signals even when not actively hungry. This suggests that the partnership may hold advantages beyond immediate caloric gain, possibly reinforcing territory control or increasing future hunting opportunities. Groupers too seem to recognize when a moray is particularly efficient. They preferentially signal individuals known to join hunts reliably, demonstrating a rudimentary form of partner choice. Such behavior places this alliance among the most cognitively intriguing interspecies interactions in the ocean. It implies memory, evaluation, and strategic decision-making. Within the broader reef ecosystem, the moray grouper partnership exerts pressure on prey populations, influencing the distribution of small fish across coral terrain. Prey species may shift their sheltering strategies, avoiding zones where cooperative hunting is common, and instead concentrating in areas where morays lack accessible crevices or where groupers face competition from larger predators. This reshaping of prey behavior creates ripple effects throughout the food web, altering nutrient flow, predator-prey dynamics, and the competitive interactions of other hunters. The moray eel itself remains a misunderstood creature. Its reputation as an aggressive predator comes primarily from its appearance and its gape, not its actual behavior. Morays prefer ambush to pursuit, concealment to confrontation. They rarely leave their shelters without strategic purpose. Their skeletal structure lacks the rigid interlocking bones seen in many fish, causing their movement to seem serpentine and eerie. But this flexibility is essential for their hunting role in cooperative attacks, enabling them to maneuver through fractured coral corridors with precision. Their cryptic coloration, ranging from mottled greens and browns to electric blues and yellows, renders them nearly invisible against the reef substrate, helping them maintain the element of surprise. Their jaws, however, remain the defining trait. When a moray strikes inside a crevice, both sets of jaws lock onto prey, with a combination of mechanical leverage and muscular contraction that few reef fish can escape. The pharyngeal jaws extend forward like a second mouth, securing prey and dragging it backward into the eel's throat. This mechanism prevents prey from slipping free in the confined spaces where the eel often hunts. In the end, the moray eel's place in the reef is not defined merely by its stealth or its anatomical innovations, but by its willingness to cooperate across species lines. The hunting alliance with groupers demonstrates that evolution can shape not only bodies and instincts, but relationships. These partnerships, formed through mutual benefit rather than familial ties, show how survival can hinge on communication between predators that share no lineage. The moray eel, hidden in its coral maze, becomes more than a solitary hunter. It becomes a critical half of a dual-organism hunting unit, one that transforms the reef from a collection of isolated niches into a dynamic arena where predators combine abilities to increase their efficiency. In this interplay of muscle, instinct, and ancient anatomy, the reef reveals a truth about life beneath the waves. Success does not always belong to the strongest or the fastest, but often to those who understand how to merge their strengths with another. The moray, with its sinuous body and double jaws, and the grouper, with its explosive power and keen vision, form a partnership that demonstrates the ocean's capacity for cooperation even among its fiercest hunters. In the soft blue haze of an early reef morning, when beams of sunlight filter down in pale columns and the water carries the muted crackle of distant shrimp, a shadow glides along the coral buttresses with the confidence of a creature that has mastered its environment. The grouper, thick-bodied and silent, moves not with the aimless wandering of a scavenger, but with the strategic deliberation of a hunter that understands both the terrain and the other predators who share it. Instead of slipping into crevices or weaving through coral branches, the grouper prefers the open corridors and the outer edges of the reef, where it can observe from a vantage point. With broad, forward-facing eyes and a heavy body built for bursts of speed rather than endurance, the grouper is a creature designed for calculated strikes. But what sets it apart is not its strength, it is its mind. Groupers are not solitary in the way many large reef predators are. They do not depend solely on instinct or brute force. Instead, they navigate their environment with a remarkable ability to recognize opportunity, to remember past experiences, and perhaps most surprisingly, to recruit assistance when the situation calls for a skill they do not possess. While many predators are defined by the limits of their bodies, the grouper expands its reach by leveraging the abilities of others. It behaves not like a lone hunter, but like a general on the reef, one that calls upon allies when the battlefield shifts out of its favor. This begins with communication. Groupers have developed a cross-species signaling repertoire that allows them to initiate cooperative hunts with moray eels, octopuses, and even the formidable Napoleon wrasse. Their most recognizable signal is the rapid headshake, a deliberate, repeated sideways movement performed while facing a potential partner. When directed at a moray eel, this gesture means a simple thing. Prey is sheltering in the coral, and the grouper needs the eel's serpentine flexibility to extract it. But this is only one entry on the grouper's list of recruitment strategies. The same grouper that signals an eel to flush out hidden prey may choose a different partner entirely when faced with another kind of challenge. Consider the Napoleon wrasse, a massive fish with a prominent forehead ridge and a jaw strong enough to crush hard-shelled prey. Some of the toughest organisms on the reef, giant clams, armored crabs, and thick-shelled snails, are beyond the grouper's capacity to break open. While the grouper can catch such prey, it lacks the crushing power to access the meat inside. Instead of abandoning the prize, it seeks assistance. In observed interactions, groupers will hover near a Napoleon wrasse and perform a distinct pointing gesture with their bodies, orienting their heads toward the hidden prey or the clams embedded in the reef. The wrasse responds not to the head shake used for morays, but to this directional cue. The wrasse approaches, delivers a crushing bite that shatters the target organism, and both predators feed, sometimes together, sometimes separately. The grouper's role is not purely parasitic. It often initiates the discovery and exposes the prey. In doing so, It demonstrates a flexible recruitment strategy based on selecting the partner best suited to the task at hand. This variability in cooperation is one of the most compelling aspects of grouper cognition. Experimental studies have shown that groupers not only form partnerships, but remember which partner performs best in specific scenarios. In controlled trials, groupers given a choice between two moray eels, one that cooperated effectively and one that did not, consistently selected the more reliable partner in repeated sessions. This shows a level of social memory that surpasses simple conditioning. The grouper retains information about individual effectiveness and uses that memory to make future hunting decisions. This, in essence, forms a mental contact list, a repertoire of preferred allies for different situations. In the chaotic world of the reef, where predatory opportunities are brief and prey vanish quickly into shelter, this ability gives groupers a formidable advantage. When a prey fish darts into a maze-like coral structure, the grouper does not waste energy attempting to dig it out. Instead, it immediately seeks the moray eel. When prey hide inside shells or cling to rocks, the grouper summons the Napoleon wrasse. When prey wedge themselves into tight, collapsible crevices, some groupers even call upon octopuses, masters of squeezing into impossible spaces. Their arms maneuver delicately into cracks, and few prey can evade their tactile intelligence. Each partner brings a unique skill set, and the grouper's intelligence lies in knowing which one to activate. In the field, this pattern reveals itself in the grouper's movement. A grouper scanning for prey moves slowly, methodically. But the moment a prey item slips into a crevice, the grouper's behavior shifts sharply. It swims directly toward a moray's shelter, sometimes traveling considerable distance. It performs the headshake signal repeatedly, often adding a hovering posture that indicates urgency. If the eel emerges, the two begin the coordinated ambush that traps prey between the eel's interior reach and the grouper's open water acceleration. But if the eel refuses, perhaps due to satiation or disinterest, the grouper does not simply give up. It returns to the shelter intermittently, repeating the signal, or it moves on to search for another eel. This persistence, repeated signaling attempts over extended periods, shows a determination rooted in strategy rather than instinct alone. This behavior becomes even more striking when groupers engage in joint hunts with multiple partners across different phases of a feeding session. There are documented observations of a single grouper recruiting a moray eel to flush prey from a crevice, capturing a fish that escapes into open water, and then immediately signaling a Napoleon wrasse to crack open a shelled organism discovered moments later. Each recruitment is targeted, specific, and timed according to environmental need. Groupers do not simply hunt, they orchestrate. At the level of sensory biology, groupers possess key adaptations that enable this role. Their eyes are large, allowing for far-reaching visual detection. Their lateral line system, a sensory organ that detects water vibrations, helps them locate hidden prey, as well as identify the movement signatures of their potential partners. This allows a grouper to distinguish between the approach of a moray eel, the powerful push of a wrasse, or the delicate motion of an octopus. Visual cues alone are insufficient in the complex visual maze of a coral reef. Vibration patterns help groupers keep track of their partners during hunts, even when visibility drops due to silt, or when prey movement creates distraction. Their communication signals are just as complex. The headshake is only the most well-known gesture. Groupers also use body tilts, sudden orientation freezes, and directional positioning to indicate where prey have hidden. When viewed from above, these gestures form a silent language, one understood by species that otherwise share no evolutionary lineage. This cross-species communication represents an underappreciated dimension of reef ecology, one in which hunters learn to read each other's intentions without sound or scent. In terms of evolutionary reward, the grouper gains substantial benefits from this cooperative behavior. By recruiting specialists, the grouper spreads its predatory reach across environments that would otherwise escape its capabilities. Open water prey, crevice-dwelling prey, armored prey, nocturnal prey, all become accessible when the grouper uses the right ally. This reduces energetic cost and increases hunting success. particularly in areas where prey density is low or competition is intense. The reef community is shaped by these interactions. Areas where cooperative hunting is common often exhibit different prey distributions than areas where solitary hunting dominates. Prey species learn, over generations of selection pressure, to avoid zones where groupers and morays frequently team up. They shift their migration patterns, modifying the timing of their foraging and the shelters they choose. This changes the distribution of nutritional flow, creating clusters of prey density in areas where cooperative predators are absent. The reef, therefore, becomes a dynamic landscape of avoidance and exploitation, influenced partially by the groupers' strategic behaviors. At dusk, when the water cools slightly and the light thins into the long shadows of coral spires, groupers often continue their patrols. Their eyes adjust to the changing light, and the reef creatures behave more erratically as night predators awaken. During this transitional period, the groupers' ability to recruit allies becomes even more critical. Moray eels, now fully active, respond readily to headshake signals. Octopuses emerge to forage, making them easier to recruit. Napoleon wrasses begin their final feeding runs before settling into the reef to sleep. The grouper becomes a node of connection in this nocturnal shift, linking species together in a web of predatory cooperation. Perhaps the most profound aspect of the grouper's behavior is its demonstration that intelligence in the natural world takes many shapes. It is not limited to the overt problem-solving of mammals, nor the social intricacies of birds. It can manifest as strategic recruitment, memory-based decision-making, and the ability to communicate across species divides. These qualities elevate the grouper from a simple ambush predator to a general of the reef, one that understands when to strike alone and when to summon allies. In this way, the grouper does not merely participate in the reef ecosystem, it actively shapes it. Its mental contact list, its cross-species language, and its partner selection strategies transform the patchwork of corals into a battlefield of opportunity. Here, intelligence is not expressed through tools or structures, but through relationships. Alliances forged not by kinship, but by shared predatory goals. The grouper, swimming slowly between coral pillars as the last light fades, carries with it a network of potential partners waiting to be activated. In the silence of the reef, without sound or spectacle, it orchestrates one of the ocean's most complex examples of cooperative behavior. And in doing so, it reminds us that predators do not always stand alone. Some command entire teams. Out in the open blue, far from the tight passageways of the coral maze, the water stretches into a vast and seemingly empty cathedral of light. Here, sunlight does not scatter in narrow ribbons, but descends in broad, wavering sheets, illuminating the suspended world of plankton, drifting larvae, and microscopic threads of life. In this immense space glides a silhouette so broad and fluid that it seems more like a drifting cloud than an animal. The manta ray, with wings spanning several meters, moves through the ocean with a grace unmatched by any other large creature. Its flight is silent, almost meditative, as though the ocean itself folds gently around its body. But even these giants, built for endurance and efficiency, depend on the reef for something essential. They come to the coral not for food or shelter, but for service, the quiet maintenance of a cleaning station. Cleaning stations form one of the most structured and orderly systems on the reef. Unlike the chaotic swirls of predator-prey chases or the shifting alliances of mobile hunters, these stations operate with steady consistency. They are marked by specific coral heads, bommies, or ledges that cleaner fish and cleaner shrimps have claimed as territory. These animals, much smaller than the clients they serve, advertise their services with bright colors or a distinctive hovering display. Their job is simple but indispensable. Remove parasites, dead skin, fungi, and accumulated debris from the bodies of visiting giants. When a manta ray approaches the cleaning station, its enormous wings slow, flattening out as though settling into a glide. The animal begins circling the area, gradually lowering its altitude until it hovers directly above the cleaning mound. At this moment, the manta transforms from a free-roaming giant into a patient client. It holds its position with remarkable precision, despite currents tugging at its broad wings. This stillness is not passive. It requires subtle adjustments, small flicks of the fin margins, tiny shifts of momentum that keep the ray suspended in place without drifting from its designated spot. Mantas do not push their way to the front of a line or force cleaners to come to them. Instead, they queue with almost ritualistic respect for the invisible hierarchy at the cleaning station. The first cleaners to arrive are often wrasses, slender, brightly colored fish with pointed snouts and quick reflexes. They begin by circling the manta's underside, inspecting the soft skin around the gill slits. These areas collect parasites that cling to the oxygen-rich currents passing through the animal's respiratory system. The cleaner fish pluck these parasites with rapid, precise bites, each removal equivalent to eliminating a potential infection site. Other cleaners move toward the wingtips where tiny copepods or skin flake clusters accumulate. Still others dart toward the head, exploring creases around the eyes and mouth. Few behaviors on the reef are as visually striking as a manta ray allowing a cleaner to enter its mouth. The ray opens its cavernous jaws, the same jaws that funnel thousands of liters of plankton-filled water each day, and holds them open patiently while a cleaner, fisher cleaner shrimp ventures inside. Here the cleaner navigates between the gill arches, picking out small worms, dead tissue, or bacteria-laden debris. This is an act of extraordinary trust. A single closing of the manta's jaws could crush the cleaner instantly. But mantas do not close their mouths during cleaning. They remain motionless, even serene. As cleaners work within a space, no other animal is permitted to enter without consequence. The manta's cooperation is a quiet demonstration of behavioral intelligence. These animals show remarkable spatial memory. Satellite tagging and long-term observational studies reveal that mantas return to the same cleaning stations year after year, often at consistent times of day or tide conditions. This fidelity suggests more than habit. It indicates that mantas encode the location and reliability of cleaning sites deeply within their long-term memory. A reef may hold dozens of coral structures that visually resemble a cleaning station, yet mantas consistently revisit only the specific sites where service has proven effective. Their enormous range, often stretching across tens or even hundreds of kilometers, does not deter them from navigating back to these precise coordinates. This pattern becomes especially evident at aggregating sites, where multiple mantas gather at once. The graceful giants establish a loose queue, circling above the body until space opens beneath them. Each manta moves forward only when the previous client has drifted off. During peak activity, the station becomes a towering column of motion, with mantas spiraling down like slow-moving leaves in an underwater vortex. The cleaners, meanwhile, work tirelessly, darting from one wing surface to another, making snap decisions about which patch of skin to treat first. This orderliness is not imposed by dominance or aggression. Mantas rarely display aggressive behavior toward one another, but by a mutual understanding of the system. The cleaning station, in this sense, becomes a place of transaction, where energy, health, and survival are exchanged across species boundaries. Cleaner fish gain a steady supply of food. Instead of hunting for small prey or competing in open water feeding frenzies, they rely on a continuous stream of clients whose bodies carry more than enough sustenance. For these small reef inhabitants, the manta ray is not a giant threat, but a floating buffet line. They depend on the consistency of cleaning behavior the way a business depends on a stable customer base. Yet for the manta ray, the relationship is equally vital. Parasites are a constant threat, particularly in plankton-rich waters where microbial life flourishes. The ray's vast surface area, soft epidermis, and constant filter-feeding movement make it an ideal host for hitchhiking organisms. Without regular cleaning, these parasites can irritate skin, interfere with hydrodynamics, or inflame gill tissue. A compromised gill system affects oxygen uptake, which in turn impacts the manta's ability to maintain long-range migrations. Cleaners, therefore, are not a luxury. They are biological maintenance workers who prevent cascading health issues. The manta's behavior at the station also reveals subtler aspects of its physiology. When holding still, the ray increases fin rigidity, reducing fluttering motions and presenting a stable platform. Its respiratory rate slows, preventing sudden bursts of water that might disturb the cleaners inside its gills. Its posture becomes symmetrical, maximizing access for cleaning. This level of control, posture, stillness, fin adjustments, requires coordinated neural and muscular effort from an animal with one of the largest brain-to-body ratios among fish. Mantas possess exceptionally developed cephalic lobes, suggesting heightened sensory processing and spatial awareness. Their ability to remember cleaning stations likely stems from both environmental mapping and social learning. Because cleaning stations are limited resources, mantas sometimes share the space with other reef visitors, parrotfish, groupers, snappers, and even green sea turtles. Each species uses cleaning stations differently. Some require only brief stops, while others spend extended sessions undergoing thorough cleaning. Mantas, with their large bodies and multiple microhabitats for parasites, often require longer sessions, yet they never force smaller clients aside. Instead, they circle, wait, and re-enter the cleaning area only when it clears. This patience stands in contrast to the aggressive dominance displays seen in many large predatory fish. The manta's size grants it physical power, but cleaning station etiquette aligns it with cooperative rather than confrontational behavior. When several mantas gather at once, the visual spectacle becomes otherworldly. Their wings overlap in vast sweeping motions, each gliding through a slow spiral that seems choreographed by some ancient instinct. Cleaners dart between them like tiny sparks of color. From a distance, the scene resembles a courtly dance, but beneath the elegance lies a deeply functional system, one that supports the health of entire populations. Healthy mantas exhibit better reproductive success, stronger migratory endurance, and lower mortality rates. The reef, in turn, benefits from their presence. As they feed on plankton and krill across wide distances, they transport nutrients and contribute to trophic regulation on a scale few other filter feeders can match. The cleaning station, therefore, becomes more than a refuge of parasite removal. It becomes a node supporting ecosystem-wide stability. There is also evidence that manta rays display individual personalities when visiting cleaning stations. Some are cautious, approaching slowly and remaining on the outer perimeter before committing to the cleaning zone. Others glide directly into position, confident and familiar with the process. Some return to the same station at precise intervals, almost like scheduled maintenance visits. Others make irregular but persistent visits, suggesting varied strategies of parasite management. These differences reflect the broader variation in manta behavior observed across their migrations and feeding patterns. They are not uniform creatures, but individuals with distinct decision-making tendencies. What makes cleaning stations particularly remarkable is how they represent cooperation without explicit communication. The manta does not signal with gestures like groupers do when recruiting moray eels. It does not negotiate terms or seek specific partners. Instead, it presents itself to the system, and the cleaners respond according to evolutionary incentives. The entire station operates on a foundation of mutual benefit, supported by finely tuned instincts and deeply encoded behaviors. The manta's return, year after year, to the same coral structure demonstrates that cooperation in the reef is not always predatory. Sometimes it is peaceful, dependable, and almost ritualistic. As the manta drifts away from the cleaning station, its skin gleams subtly in the filtered light. Its movements regain their sweeping elegance, and the giant disappears gradually into the open blue, its wings pulling it toward feeding grounds or migration routes unseen from the reef below. The cleaners, having finished their task, return to their post and await the next visitor. And the reef, momentarily quiet after the passing of such a giant, resumes its cycle of noise, color, and motion. In the open ocean, the manta ray is a wide-ranging traveler, a filter-feeding titan, and a symbol of fluid majesty. But here, at the cleaning station, it becomes something more intimate. A client seeking care, participating in a system that keeps both itself and the reef in balance. Without these stations, mantas would carry burdens that compromise their strength. Without mantas, the cleaners would lose a dependable source of food. In this delicate exchange, the reef reveals yet another of its hidden harmonies, a silent pact of cleanliness, memory, and mutual survival. Far from the gentle rhythms of reef cleaning stations and the coordinated dances of cooperative hunters, the open ocean carries a different soundtrack. One composed of drifting currents, long silences, and the slow decay of all things left unclaimed. Here, where nutrient pathways scatter across kilometers of blue water and death often dissolves unnoticed into the depths, one creature patrols with the steady assurance of a scavenger born to manage the ocean's forgotten remains. The tiger shark, with its broad head, heavy frame, and unmistakable vertical stripes, moves with neither elegance nor haste. It glides like a shadow stitched into the water itself, following trails that other predators ignore. The smell of rotting flesh, the churn of fishing vessels, the drifting silhouettes of weakened animals, and the faint chemical trace of dying reef life. In the marine world, the tiger shark plays the role few others can afford to embrace: the waste management system of the open sea. The ocean produces an enormous amount of organic waste. Large animals die far from shore, their bodies dropping slowly through the water column or drifting in surface currents. Turtles weaken after migrations. Fish discarded by trawlers form loose clouds of dead or injured bodies. Even a single-stranded whale contributes a massive pulse of biomass into the ecosystem, a feast too large for any one species to handle. Into this world of decay, tiger sharks move with methodical purpose. They follow scent plumes invisible to us, but mapped clearly through the shark's olfactory system. Their sense of smell, refined over millions of years, allows them to detect dead or dying animals from extraordinary distances. Once the scent is detected, the shark adjusts its path, often traveling in a straight, unwavering line toward the source. These journeys are not random scavenging quests, but structured contributions to ecological balance. When a whale carcass drifts near a coastline or grounds itself on a shallow bank, tiger sharks become first responders. They consume large portions of decaying tissue, converting what would otherwise rot and release excess nutrients into a stable, predatory cycle. The biomass becomes shark muscle, shark energy, and shark growth, instead of becoming an uncontrolled nutrient dump that might trigger algal blooms or suffocate local waters. This transformation, from decay to predator, is a critical service in ecosystems with limited nutrient sinks. Without tiger sharks and other large scavengers, the ocean's waste would accumulate in ways that destabilize water chemistry, bacterial communities, and coastal habitats. Tiger sharks are not selective. Their diets span a vast range: sea turtles, rays, dead seabirds, injured fish, carrion, even the byproducts of human fishing activities. Because of this generalist diet, scientists once described them as garbage cans of the sea, though the term oversimplifies their role. A garbage can collects, a tiger shark processes. It actively recycles and redistributes nutrients, preventing localized overload. This metabolic function has cascading ecological effects, particularly in the coastal ecosystems where tiger sharks frequently patrol. One of the most profound indirect alliances forged by tiger sharks exists between the sharks, sea turtles, and seagrass meadows. Green turtles are powerful grazers. In large numbers, they can mow down seagrass meadows far faster than the plants can regenerate. Without predators, turtle populations expand and shift into grazing patterns that degrade seagrass habitat. Entire meadows can collapse into barren sand plains, disrupting ecosystems that rely on dense, healthy seagrass beds. These meadows are nurseries for juvenile fish, feeding grounds for dugongs, stabilizers of sediment, and some of the most efficient carbon sinks in the marine biosphere. Tiger sharks, by preying on turtles, and just as importantly by simply being present, reshape this dynamic. Their presence alters turtle behavior. Studies in places like Shark Bay show that turtles modify their grazing patterns when tiger sharks patrol nearby. Instead of grazing openly in exposed areas, turtles seek refuge within the safer zones of complex seagrass beds or forage in smaller, more cautious bites before moving to new patches. This landscape of fear prevents turtles from overgrazing any single area. The effect is not heavy predation, but behavioral pressure. The threat of tiger sharks spreads turtle foraging across a wider area, allowing seagrass to regenerate. This indirect deal between tiger sharks and seagrass meadows unfolds without conscious negotiation. The shark does not protect the meadow. The meadow does not feed the shark. But the interaction forms a system of checks and balances that supports countless additional species. Dugongs thrive when seagrass meadows remain robust. Juvenile fish, hiding among the blades, experience higher survival rates. Carbon stored in the seagrass roots remains locked away instead of released into the water column. The tiger shark, by imposing predation risk on turtles, becomes a keystone regulator of carbon storage and coastal stability. This role reveals one of the ocean's most striking truths. Sometimes the least refined, least delicate species performs the most essential work. The tiger shark's wide-ranging behavior extends far beyond turtle management. These sharks often shadow fishing fleets, consuming discarded bycatch before it can sink and decompose. In some regions, they track migratory herds of turtles, dolphins or rays, acting as mobile top-level recyclers. In other scenarios, they focus on dead whales, massive carcasses that form the largest single meals available in the ocean. Tiger sharks arrive early in the succession, stripping away the soft tissue before scavengers like deep-sea amphipods and bacteria take over. When tiger sharks reduce the bulk of the carcass quickly, fewer nutrients fall rapidly to the sea floor, altering the rate at which deep ecosystems receive this nutrient pulse. In this sense, they influence the vertical speed of energy movement through the entire water column. Their presence also shapes the behavior of other predators. When tiger sharks patrol shallow waters, mid-level predators such as rays, smaller sharks, and certain large fish avoid the area. This redistribution alters predatory pressure on species like crustaceans, cephalopods, and bony fish. In ecosystems with healthy tiger shark populations, mid-level predators do not dominate seagrass meadows or coral flats. They do not overhunt young fish or collapse small prey populations. The result is a layered food web with stability built into its structure. Remove the tiger shark, and the balance tips sharply. Rays multiply, digging up seagrass and disturbing sediments. Turtles graze without restraint. Fish nurseries shrink. A chain reaction unfolds. This ripple effect was documented dramatically in Shark Bay, when a climate-induced decline in tiger shark visitation altered turtle behavior. With fewer sharks patrolling the meadows, turtles expanded their grazing, concentrating in vulnerable areas. Over time, sections of seagrass habitat collapsed, reducing the nursery space available for fish species and altering the behavior of dugongs. The decline cascaded into losses in biodiversity and shifts in nutrient cycling. In essence, the removal of a single top predator destabilized the entire system. This is the invisible power of the tiger shark. It does not build reefs or clean them. It does not engineer environments like parrotfish or stabilize them like corals. But it controls the distribution of pressure across ecosystems, preventing overgrowth and overuse. Tiger sharks also perform a role that is increasingly recognized in conservation science, converting dead biomass into mobile biomass. When a creature dies in the ocean, its energy remains trapped unless consumed by scavengers. If it decomposes slowly, bacteria and microbes use the nutrients locally, potentially leading to harmful blooms or hypoxic pockets. But when a tiger shark consumes that biomass, it becomes part of a mobile predator that spreads nutrients through excretion, movement, and predatory cycles across large distances. This mobility redistributes nitrogen and phosphorus across coastal and pelagic areas, effectively smoothing nutrient spikes that would otherwise remain concentrated. The movement of tiger sharks across oceanic regions turns scattered patches of decay into broad ecological benefit. Their foraging behavior is shaped by sensory precision. Tiger sharks possess electroreceptive organs known as ampullae of Lorenzini, which allow them to detect the faint electrical fields emitted by living or recently deceased animals. They track scent trails through chemosensory detection, using the gradient of odor concentration to move directionally toward carrion. They rely on vision only once they close in, because most of their work occurs in low visibility environments, at night, or in vast pelagic waters where contrast is minimal. Their responses to stimuli reveal a biological design tailored not only to active predation, but to locating hidden or decaying biomass. Despite their ecological importance, tiger sharks exist in an uneasy relationship with human activity. Fishing lines and nets catch them unintentionally. Longline fisheries targeting tuna and swordfish often attract tiger sharks due to the scent of wounded prey. Their scavenging tendencies, the very habits that maintain ocean cleanliness, become liabilities near human-made debris. Yet even here, the sharks perform a service. They consume fish waste that would otherwise contribute to coastal eutrophication or attract dangerous aggregations of smaller scavengers. Their presence near shorelines, though sometimes feared, is a sign of a functioning marine system, one where waste is quickly converted back into living biomass rather than accumulating dangerously. When seen from above, the tiger shark's roaming patterns resemble the sweeping vacuum routes of a slow, unhurried custodian. It does not chase with reckless speed. It does not rely on agility or stealth. Instead, it moves with the inevitability of entropy, cleaning the ocean one carcass at a time. But the tiger shark's role extends beyond the visible. It manages the invisible threads of ecological stability, the distribution of grazing pressure, the pace of nutrient recycling, the maintenance of seagrass meadows, and the prevention of waste accumulation. In this quiet, often misunderstood predator, the ocean finds balance through brutality. The tiger shark does not form friendly alliances, nor does it negotiate bonds of cooperation. Its deals are implicit, forged through the logic of evolution rather than empathy. Turtles graze carefully because the tiger shark exists. Seagrass meadows flourish because turtles graze carefully. Dugongs thrive because seagrass meadows flourish. Carbon sinks deepen because dugongs and meadows persist. And fish nurseries remain safe because the structural integrity of those meadows remains intact. All of this happens because a striped predator continues its slow, steady patrol. In the tiger shark, the ocean's waste disappears. In its wake, the ecosystem holds together. In the warm shallows of a coastal bay, where the morning sun paints the water's surface with bands of silver and pale green, a ripple cuts across the calm like a brushstroke of intention. A bottlenose dolphin rises, exhales a soft plume of mist, and disappears again beneath the surface. Around it, faint shadows shift in a coordinated pattern. Not random bursts of motion, but the beginning of a hunt. Dolphins are rarely alone. They move through the ocean as members of fluid societies, bound together by an intelligence that has evolved through millions of years of cooperation. Their success as predators does not hinge on speed alone, nor on physical power. It hinges on teamwork. Teamwork not only among themselves, but across species boundaries, forming alliances that stretch far beyond what most marine animals can perceive. The dolphin's world is built upon sound. As it glides through the shallows, it emits bursts of clicks, high-frequency pulses that bounce off fish, sand ridges, shells, and the movements of its companions. These echoes build a three-dimensional acoustic map, revealing not only where prey hides, but where fellow dolphins position themselves in the unfolding plan. For bottlenose dolphins, hunting is not a simple chase. It is a choreography. They herd fish the way sheepdogs guide livestock, reading each other's movements with a sensitivity that stretches beyond visual cues. Their formations shift continuously as the fish regroup, scatter, or attempt escape. Each dolphin adjusts its angle, speed, and vocal patterns, forming a dynamic, living network of coordination. One of the most dramatic displays of such coordination occurs in coastal regions, where dolphins perform a hunting behavior known as beaching or strand feeding. In these moments, dolphins accelerate toward shallow banks, driving schools of mullet or small fish directly onto sandbars. The chase happens in seconds. Dolphins surge forward in a tight arc, pushing walls of water that trap the fish against the rising shoreline. Then, with a burst of speed, they propel themselves partially out of the water onto the sand, snapping up the stranded prey with precision. It is a high-risk maneuver. A poorly timed push could leave a dolphin beached too high, unable to slide back into deeper water. Yet entire pods perform this coordinated behavior with careful timing, learning the craft over years. Younger dolphins observe older ones, practicing tentatively until they have mastered the timing, the angle of approach, and the exit technique. These hunts succeed not because of individual skill alone, but because of shared knowledge passed along like cultural inheritance. In deeper waters, a different spectacle unfolds. the creation of mud ring traps. In certain regions, bottlenose dolphins use the soft sediment of the sea floor as a weapon. One dolphin circles a school of fish, beating its tail against the bottom and stirring up a dense ring of mud that rises through the water like a vertical halo. The fish, confused and surrounded by the opaque cloud, leap outward over the rim. Waiting dolphins, stationed at precise positions, snatch the airborne fish one by one. The technique requires a division of roles. One dolphin generates the ring, and several others capture the fleeing prey. It is a behavior that relies on planning, synchronized positions, and the ability to understand the movement patterns of both partner and prey. This kind of cooperation suggests cognitive abilities uncommon in most marine predators, abilities tied to prediction, problem-solving, and mutual reliance. But dolphins do not limit their alliances to their own species. In vast oceanic feeding grounds, bottlenose dolphins join forces with tuna and seabirds, forming mixed species teams that track schools of pelagic fish across enormous ranges. Tuna, with their streamlined bodies and incredible speed, drive baitfish upward in dense, panicked clusters. Dolphins, using their sonar and coordinated herding strategies, prevent the fish from escaping sideways or dispersing into deeper water. Seabirds read the cues from beneath the surface, the glittering flash of fish, the sudden surge of dolphins, and plunge into the frenzied mass from above. Each species interprets the other's movements in real time. When tuna accelerate, dolphins adjust their arc. When dolphins tighten the circle, seabirds shift position, anticipating where the fish will burst next. These alliances are not directed or planned. They emerge from behavioral compatibility, converging through mutual benefit. In these moments, the surface of the ocean becomes a multi-layered battlefield. Beneath it, dolphins sound in coordinated bursts as they push the fish into tighter spheres. At mid-depth, tuna slice through the water with whip-like efficiency, accelerating with bursts of muscle power that dolphins themselves cannot match. Above, seabirds dive repeatedly, piercing the water column with precision. Each predator reads the other's cues, not through direct communication, but through a web of sensory interpretation that links sound, motion, vibration, and light. This mixed species cooperation illustrates a universal truth of the open ocean. Survival often belongs not to the strongest hunter, but to the one that forms the most efficient alliances. Yet the most extraordinary alliance dolphins participate in is not with fish or birds. It is with humans. Along the coasts of Brazil and Myanmar, communities have practiced cooperative fishing with dolphins for generations. This relationship is neither accidental nor modern. It is a cultural institution shared between species, passed down through human families and dolphin pods alike. In these regions, fishermen wade into shallow waters with nets held ready. Offshore, dolphins patrol the entrance of the bay, herding schools of fish toward the shore. The hunt begins when dolphins approach the fishermen and give a clear signal, a dive, a splash, or a distinctive roll, indicating that the fish are within netting range. The fishermen respond instantly, casting their nets at the precise moment the dolphins signal. The net traps a portion of the fish, while the dolphins use the confusion and entanglement to catch the rest. Both parties gain from the exchange. The humans receive a bountiful catch. The dolphins receive easier access to tightly clustered prey. This system is not a simple coincidence of behavior. Studies show that the dolphins involved in these fisheries display specialized techniques and participate actively, not passively. They adjust their movements according to tide, fish density, and human timing. They recognize individual fishermen and show preferences for particular boats or families. Fishermen, in turn, identify individual dolphins by scars, fin shapes, or behavioral patterns, knowing which ones are reliable partners. This cross-species alliance requires communication that spans the boundary between human and marine cognition, an alignment of behavior that only works because both species understand the basic rules of cooperation. In Brazil's Laguna region, this partnership has persisted for more than a century, with oral histories stretching back through multiple human generations. Dolphins there inherit the tradition from their elders. calves learn the signals by watching their mothers interact with fishermen, gradually joining the cooperative hunts as they mature. When dolphins stop participating, the fishery's success rates decline sharply, demonstrating how deeply the system depends on the dolphin's consistency and intelligence. These interactions represent one of the rarest phenomena in the animal kingdom, a stable, intergenerational alliance between wild animals and humans maintained without captivity, training, or domestication. Across the world, bottlenose dolphins also form ephemeral alliances with sharks, using their agility and group coordination to outmaneuver predators, while capitalizing on the disturbances sharks create in prey schools. They sometimes shadow whales, exploiting krill movements stirred by massive fins. They interpret the motions of diving seabirds as indicators of hidden fish. They read the ocean, the way a skilled navigator reads shifting currents, not as a static environment, but as a stage filled with players whose movements reveal opportunity. What makes dolphins extraordinary is the depth of their social coordination. Their pods are not rigid structures, but fluid groupings that shift according to age, experience, food availability, and social bonds. They form alliances reminiscent of primate coalitions, with individuals cooperating during hunts, competitions, or migrations. They transmit complex foraging techniques across generations, forming cultural traditions unique to each population. They recognize each other by signature whistles, acoustic names embedded within their vocal repertoires. These social frameworks underpin their hunting success. A dolphin pod, functioning as a unit, becomes a mobile intelligence network capable of adjusting strategies based on dynamic conditions. In many ecosystems, dolphins act as regulators of mid-level fish populations. Their pursuit of schooling species influences the movement patterns of entire prey communities, redistributing grazing pressure and shaping the energy flow of the system. When dolphins participate in mixed species hunts, their presence can accelerate the collapse of bait balls, reducing the time predators need to secure food. When they join human fisheries, they alter the distribution of fish near coastal settlements. When they form beaching teams, they influence shoreline nutrient deposition by redistributing prey remains. Their hunting behaviors, though seemingly localized, contribute to broader ecological patterns. From an evolutionary standpoint, the dolphins' alliances reflect a strategy based not on brute force but on adaptability. Their greatest weapon is not their jaw strength or speed, but their ability to read the intentions of others, be they tuna, seabirds, or humans, and respond with intelligent coordination. Their cooperation is not a matter of chance. It is the product of cognitive evolution shaped by social living, long lifespans, and flexible feeding strategies. As the day fades and the coastal waters turn from green to deep blue, a pod of bottlenose dolphins continues its patrol. Some peel off to join diving seabirds chasing anchovies. Others regroup in shallower water where mullet schools shimmer in the dusk. Their hunting strategies shift effortlessly with the setting sun, responding to cues from other animals that share their ecosystem. And somewhere in the world, human fishermen wade into a muddy river mouth, waiting for a familiar signal, the splash of a dorsal fin breaking the still water, that tells them their ancient partners have arrived. In the story of ocean predators, the bottlenose dolphin does not stand alone. It stands at the crossroads of species, a hunter that builds bridges, reads intentions, and turns cooperation into a survival strategy. Its alliances, whether with fish, birds, dolphins, or humans, demonstrate that intelligence in the sea is not just about knowing where to hunt, but about knowing whom to hunt with. In the cold, steel-blue waters of the temperate ocean, where the horizon blurs into mist and the surface heaves with long, rhythmic swells, a black dorsal fin slices upward like the blade of a surfacing submarine. It moves with deliberate steadiness, cutting a clean path through the water before disappearing again beneath the dark surface. This is the orca, a creature so intelligent, so adaptive, and so influential that entire ecosystems shift under the pressure of its decisions. More than a predator, more than a hunter, the orca functions as a strategist. Each pod operates not merely as a group of individuals, but as a cultural unit shaped by traditions learned over generations. They are often called wolves of the sea, but in many ways they are something more. Engineers of ecological order, whose choices ripple downward through every level of the marine ecosystem. Orca societies are built on culture, a rarity in the animal kingdom. Each pod possesses its own dialect of calls, its own hunting techniques, even its own dietary specialization. In some regions, one pod targets seals, another prefers salmon, and another hunts larger whales. These distinctions are not genetic differences, but cultural traditions passed from mothers to calves, reinforced through years of learning, practice, and shared success. As a result, orca populations that share the same waters may live entirely different ecological lives, sometimes avoiding each other as neatly separated as different tribes. In the subpolar oceans, one pod may patrol the kelp-lined coastline, hunting seals that rest on ice floes or rocky outcrops. Their strategy is cooperative and precise. Several orcas surge forward simultaneously, generating waves that wash seals from their safe perches into the water below. Others wait at the base of the wave, ready to intercept the falling prey. This wave-washing technique is not instinctual. It is taught. Calves learn to position themselves correctly, practicing smaller waves until they can contribute to the coordinated surge. The behavior spreads through the pod like a skill passed down in a family of craftsmen. In other regions, orcas employ a completely different repertoire. Offshore pods, often traveling far from land, target sharks. They exploit the shark's need to maintain constant forward motion. By flipping a shark upside down, the orca induces tonic immobility, a temporary paralysis triggered by disorientation. Once flipped, even powerful sharks become helpless. Orcas then extract the liver, an energy-rich organ filled with oils, leaving the rest of the carcass to drift away. This surgical precision shows an understanding of anatomy and technique that emerges only in long-lived, socially cohesive species. But perhaps the most dramatic orca hunting culture belongs to the pods that specialize in hunting great whales. These orcas do not operate in stealth or speed, but in overwhelming coordination. When they encounter a young baleen whale traveling with its mother, the pod begins a series of flanking attacks. They isolate the calf, exhaust the mother, and block her attempts to lift the calf to breathe. The struggle can last hours. This hunting strategy requires not only physical endurance, but communication, memory, and strategic placement of individuals across many meters of turbulent water. Despite the savagery of these scenes, orcas also form loose, opportunistic alliances with other species. When a large whale carcass sinks slowly toward the seabed, sharks, seabirds, and orcas converge. While sharks tear into dense muscle, seabirds pick at floating fragments, and smaller fish swarm the area. Orcas take the choicest cuts, typically the lips, the tongue, or the nutrient-rich organs. They tolerate the presence of other scavengers, not because of friendliness, but because their own strategy involves consuming high-value tissues and moving on. The leftovers support dozens of other species. These moments reveal something fundamental. Orcas influence not only the act of predation, but the broader distribution of nutrients in the ocean. This influence extends beyond the immediate kill. Orcas shape ecosystems through what ecologists call trophic cascades, chain reactions that begin with an apex predator and cascade downward to influence plants, algae, and habitat structure. One of the most striking examples comes from the Northeast Pacific, where the decline of great whales due to centuries of whaling forced orcas to alter their diet. Historically, orcas in these waters fed mainly on large baleen whales. But as those whale populations collapsed, orcas shifted to smaller marine mammals, first seals, then sea lions, and eventually sea otters. Sea otters, once abundant in kelp forests, became primary prey for orcas hungry for high-calorie food sources. As otter numbers declined, their grazing pressure on sea urchins weakened. Sea urchins, powerful herbivores in their own right, exploded in number. Without otters to eat them, the urchins consumed kelp stems with relentless efficiency, transforming once lush kelp forests into underwater deserts known as urchin barrens. What began as a shift in orca diet rippled through the ecosystem, until the very architecture of the coastal ocean changed. Fish nurseries disappeared. Biodiversity plunged. Even carbon storage declined, because kelp forests act as major sinks for atmospheric carbon. A single change at the apex of the food web rewired the entire seafloor. This story has repeated in multiple ecosystems, each demonstrating the same principle. When orcas adjust their alliances or shift their prey, ecosystems reorganize. In regions where orcas feed primarily on salmon, their presence influences the behavior of sea lions and seals, who in turn modify their foraging around salmon streams. If salmon decline due to overfishing, dams, or warming waters, orcas lose their primary resource and shift pressure to alternative prey. These shifts cascade through fish populations, altering species composition and competition dynamics. A reduction in salmon also impacts forests. Salmon carcasses brought ashore by predators enrich forest soils with marine nutrients. Orcas, by regulating seal populations that prey on salmon, indirectly influence trees miles inland. In other areas, orcas affect seabird populations by competing for the same fish stocks. In some places, their presence displaces other predators, altering where birds choose to nest or forage. Seabird colonies depend on the abundance of fish near breeding grounds. When orcas shift fish distributions through predation or competition, seabirds adapt their nesting behavior, sometimes relocating entire colonies. These shifts influence nutrient deposition on islands, shaping vegetation and soil composition. Through these mechanisms, orcas, animals that rarely touch land, influence landscapes. Their role as apex strategists becomes even more evident when examining what happens in their absence. In areas where human intervention has removed or displaced orcas, mid-level predators often surge. Seals, sea lions, and smaller sharks expand into territories once patrolled by orcas. They apply heavier pressure on fish populations, sometimes collapsing local fisheries or unbalancing the ecosystem. Without the regulating effect of orcas, prey species concentrate in vulnerable areas, altering competition patterns. The underwater landscape of fear disappears, and with it the spatial balance that once sustained the system. What makes orcas unique among apex predators is their combination of intelligence, cultural transmission, and ecological impact. Wolves shape landscapes on land through their influence on herbivores. Lions structure savannas by regulating grazing animals. But orcas, with their far-reaching migrations and diverse hunting cultures, influence ecosystems across a vastly greater scale. From the surface down to the kelp forests, from coastal shallows to pelagic depths, from fish to mammals to nutrient cycles. Their ability to reshape food webs arises not only from their power, but from their flexibility. When prey becomes scarce, orcas shift tactics. When environmental conditions change, they alter their routes. When one prey population declines, they move on to another. Each change reverberates through the system. Their alliances, whether with seabirds scavenging at carcasses, sharks circling kills, or even humans hunting whales in past centuries, mold ecosystems through both cooperation and conflict. In many ways, orcas are the ocean's quiet managers, architects of balance who never consciously design, yet whose actions define structure. They do not construct reefs, plant kelp, or nurture seagrass. Yet their decisions determine whether these habitats thrive or collapse. Through predation, through scavenging, through cultural continuity, orcas maintain an equilibrium that no other marine species can replicate. As an orcapod passes through the dimming light of a high-latitude afternoon, the water around them turning colder and darker, their silhouettes form a shifting line of deliberate movement. Each breath breaks the surface in a soft burst of vapor. Each dive sends them deeper into the layered world of the ocean. Below them, seals alter their routes. Sea urchins feed more cautiously. Salmon shift their schooling patterns. Kelp forests sway intact or stripped according to the orca's choices. Their influence is a shadow cast long across the ecosystem, silent, unseen, but unmistakable. These are not simply predators. They are strategists operating across generations. And when they act, the entire ocean listens. The surface of the temperate ocean rolls beneath a slate-colored sky, each swell lifting and falling with the slow pulse of a giant world. In the middle of this restless wilderness, a broad, mottled back breaks the surface, followed by a column of vapor that rises like a breath from the sea itself. A humpback whale exhales, lingers for a heartbeat, and sinks again into the deep. It is massive enough that the water seems to yield around it, large enough that time itself appears to slow when it moves. But beneath this calm, lumbering presence lies one of the most surprising forces in the marine world. A creature whose behaviors ripple across species, not through predation or threat, but through moments of interference, protection, and cooperation that scientists are still struggling to fully interpret. Humpback whales, unlike orcas, are not apex predators. They do not stalk, chase, or attack other marine mammals. They are filter feeders, harvesting krill and small schooling fish through a combination of strategy and sheer bulk. Yet humpbacks consistently and repeatedly intervene in orca hunts around the world, sometimes placing themselves directly between attacking orcas and the targeted prey. These interventions occur so often, in more than 100 documented events, that the pattern has become one of the strangest puzzles in marine behavioral science. An orca hunt unfolds with precision and violence. When orcas isolate a grey whale calf from its mother, the chase can extend for kilometers. The mother pivots and strikes, using her massive tail to fend off attackers, while the calf exhausts itself in a desperate attempt to remain close. The surface churns with foam and blood. The cries of the calf echo through the water column. In these moments, a humpback whale may suddenly appear at the edge of the conflict. Sometimes a pair arrives. Occasionally, a dozen or more humpbacks converge, emerging from distant feeding grounds as though drawn by a signal that no instrument can detect. Researchers following these events report humpbacks positioning themselves between the orcas and the calf, swinging their giant pectoral fins, each fin longer than a grown human, to repel the attackers. The whales produce loud, trumpeting exhalations and slap their fins against the surface with thunderous force. The orcas, agile but wary of injury, often divert their strategy, sometimes abandoning the hunt entirely. The humpbacks gain nothing directly from these interferences. They do not feed on the prey or gain any obvious survival advantage. Yet cases continue to accumulate. Humpbacks protecting seals hauled onto ice floes, humpbacks shielding porpoises, humpbacks even defending sunfish from orca harassment. One theory proposes simple, misdirected behavior. Humpbacks respond to predator distress cues because those cues resemble those of their own calves. But that explanation does not fully fit the data. Many humpback interventions occur far from calf rearing seasons. Others involve humpbacks who show no sign of parental experience. Another theory suggests an evolutionary remnant, an instinctive drive to disrupt orcas as a protective measure for their own species. Humpbacks, after all, have long been prey for orcas, especially young calves who remain vulnerable during migration. Interrupting orca hunts might reduce future threats to humpback infants. But this too remains incomplete, because humpbacks often intervene on behalf of species that share no danger relationship with them. Whatever the cause, the effect is unmistakable. Humpbacks act as accidental bodyguards across multiple marine ecosystems. Their presence frustrates orca hunting strategies, protects vulnerable species, and creates temporary alliances with prey animals who seem as astonished by the rescue as any observer. These interactions demonstrate that influence in the ocean is not limited to apex predators. Sometimes the most unexpected species shape survival dynamics through sheer size, timing, or behavioral quirks that defy traditional categories. Yet the humpback whale's ecological significance extends far beyond orca interference. In other moments, they become not protectors, but architects of one of the most sophisticated feeding strategies in the animal kingdom: bubble net feeding. This behavior, unique to certain humpback populations, illustrates how collaboration, whether deliberate or emergent, can transform the ocean into a multi-species banquet where birds, fish, whales, and even dolphins use each other's movements to amplify success. Bubble net feeding begins with a dive. A group of humpbacks sinks into the dark, silent depths beneath a school of fish, dropping far enough that the water turns cold and the light dims into blue twilight. Then, at a precise moment, one whale begins to circle upward, releasing a continuous stream of bubbles through its blowhole. The bubbles rise and expand, forming a cylindrical wall around the schooling fish. This net, made of nothing but air, corrals the fish into an ever-tightening sphere. The fish, confused by the barrier and sensing the sudden rise in pressure and light distortion, cluster together in fear. Meanwhile, the whales coordinate from below, each taking their assigned role. Some circle to maintain the bubble wall. Others position themselves at the base, ready to lunge. As the bubble ring narrows, the whales surge upward in a synchronized column. Their vast mouths open, revealing baleen curtains that filter thousands upon thousands of fish in a single ascent. A single lunge can capture more biomass in seconds than most predators acquire in hours. But the miracle of bubble net feeding is not the technique itself. It is how many species participate in the event, each in its own manner. Above the surface, seabirds, shearwaters, gulls, terns, and cormorants hover, watching the subtle cues that signal where the whales will lunge. They read the movement of baitfish that scatter at the bubble ring's edge. They watch for the slight bulge in the water that forms moments before the whales break through. When the whales rise, mouth agape and bodies churning through the surface, fish leap skyward in desperation, providing a feast for the waiting birds. Below the surface, smaller predatory fish such as salmon or mackerel hover nearby, drawn to the panic vibrations of the trapped school. Dolphins sometimes join the periphery of the net, feeding on fish that escape sideways, or using the whale's movements as cues for where prey density is highest. Even seals may linger at the edges, grabbing stragglers that slip between the cracks in the whale's coordination. This is not a partnership in the deliberate sense. The humpback whales do not create bubble nets for the benefit of birds or dolphins. They do not invite other species to join them. Yet the system operates like a loose alliance, a shared exploitation of opportunity. Each species reads the signals produced by the others, adjusting its hunting strategy based on the predictable rhythm of the whales. The birds listen for whale exhalations and search for tight fish schools. The dolphins follow the vertical surges. The whales themselves rely on the chaotic behavior of fish when compressed by the presence of multiple predators. The deal, if it can be called that, emerges from alignment, not intention. By targeting the same prey, the movements of each species guide the success of the others. Bubble net feeding demonstrates the humpback's capacity for cultural behavior. Not all humpback populations perform this maneuver. It is specific to certain regions, taught from whale to whale through observation, practice, and repeated exposure. Young whales learn their roles gradually, often participating at the periphery before joining the full circle. The complexity of the technique requires coordination among multiple individuals, each contributing a unique motion. The bubble blower, the caller, the lungers. Their calls, produced in the depths, may help align timing or synchronize lunges. The behavior suggests a level of group planning unusual among filter-feeding mammals. When viewed from a distance, the surface seems to erupt in a controlled explosion. The circle of bubbles, the burst of whale bodies, the chaos of fleeing fish, and the storm of diving birds create a single intertwined feeding event that draws energy upward from the microscopic world of plankton to the predators that rule the sky and sea. These moments highlight the humpback whale's position not as a solitary giant, but as a keystone participant in multi-species dynamics. Beyond feeding and protection, humpback whales also act as nutrient pumps in the marine environment. Their vertical migrations, diving deep to feed and returning to the surface to breathe, transport nutrients upward through the water column. Each time a whale defecates near the surface, it releases iron-rich waste that supports phytoplankton growth, fueling the base of the marine food web. Their presence enhances productivity across large regions, supporting fish populations that birds, seals, and other predators rely on. Even their carcasses, when they eventually sink, create whale falls, oases of life in the deep sea that sustain ecosystems for decades. In these ways, humpback whales contribute not only through behavior, but through their very existence, shaping the ocean's nutrient and energy flows. When humpbacks intervene in orca hunts, they act as unplanned guardians. When they form bubble nets, they become strategic partners within a temporary, multi-species feeding guild. When they migrate and defecate, they fertilize the surface waters. When they die, they create ecosystems on the seafloor. Every aspect of their lives creates ripple effects. As evening settles and the surface glows with the soft gradient of a sinking sun, a group of humpbacks gathers one last time. Their breaths lift in slow, rhythmic plumes. Below them, the fish they displaced begin to reorganize. Above them, birds continue circling, hoping for a final burst of opportunity. For a moment, the entire scene becomes a quiet convergence of species, each responding to the presence of the whales, each adjusting its strategy in the fluid dance of the marine world. The humpback whale may not be a predator. It may not be an apex hunter. But through its actions, intentional or accidental, it reshapes the ocean around it. A protector one moment, a feeding architect the next, a nutrient transporter always, and a cornerstone of life, even in death. In the vast, interconnected wilderness of the sea, few creatures influence as many species, in as many ways, as the humble giant that rises and falls with the tides. The coastal waters of the North Pacific carry a different temperament from the open sea. Here, the surface is rarely still. Waves roll inward across rocky shorelines, tangling themselves through long fronds of kelp that sway beneath the surge like living banners. Sunlight filters downward in shifting columns, turning the underwater forest into a green cathedral. Blades of kelp stretch toward the surface, forming a canopy that softens the force of waves and provides shelter for the creatures below. Fish weave between the fronds, crabs pick along the holdfasts, snails graze on delicate algae, and countless species hide, feed, breed, and grow in this rich, three-dimensional world. But despite the power and flexibility of these underwater forests, their stability rests on a single, unlikely guardian: the sea otter. Drifting on its back, paws folded across its chest, the sea otter seems like an animal sculpted for charm rather than ecological force. Its fur, the densest of any mammal, traps pockets of air that insulate it from frigid waters. Its whiskers twitch as it scans the kelp canopy. Its body bobs lightly in the swell, seeming almost weightless. And yet beneath this disarming appearance lies a metabolism that burns energy at a relentless pace. To stay warm in the cold Pacific, a sea otter must consume a significant fraction of its body weight every day. This requirement forces otters to hunt constantly, and through that appetite, they become the keystone protectors of kelp forests. The sea otter's preferred prey is the sea urchin, a creature that grazes on kelp with single-minded persistence. An urchin may appear harmless, little more than a ball of spines rolling slowly across the sea floor, but its grazing power is immense. Each urchin uses its 5-part beak-like mouth, the Aristotle's lantern, to scrape kelp holdfasts from their anchors. 1 or 2 urchins create only minor damage, but entire populations can transform forests into wastelands. An uncontrolled urchin population eats through kelp as efficiently as locusts devour plants on land. Without predators to restrain them, they multiply rapidly and consume kelp until all that remains is bare rock. Sea otters sever this destructive chain. They patrol kelp forests, using their sensitive forepaws to feel for hidden urchins among rocks and holdfasts. When an otter finds one, it grasps it delicately, flips onto its back, and uses its strength and specialized teeth to crack open the shell. Sometimes it uses a tool, a carefully selected rock stored in the loose skin pouch beneath its forearm. Floating calmly, the otter places the rock on its chest and pounds the urchin against it, generating a hollow, clacking sound that echoes through the water. In these moments, a visitor would never suspect that this simple act is saving an entire ecosystem. Through predation alone, sea otters prevent urchin populations from expanding uncontrollably. They keep grazing pressure on kelp manageable, allowing plants to anchor, grow, and form dense underwater forests. These forests, in turn, support an astonishing diversity of life. Juvenile rockfish shelter among the blades, avoiding predators that patrol open water. Snails crawl along the kelp surface, feeding on algae that would otherwise smother the blades. Crabs scuttle through the dim undergrowth, competing for territory within the forest floor. Even sea stars, abalone, and octopuses depend on the complex structure that living kelp provides. More than 1,000 species may inhabit a single healthy kelp forest, each forming a thread in the broader ecological tapestry. The strength of this indirect alliance, otter, urchin, kelp, and hundreds of other species, lies not in cooperative behavior, but in ecological balance. The otter does not intend to safeguard forests. It does not choose to be a guardian. It simply hunts to survive. But the effect of its hunting radiates outward, shaping the structure of the entire coastline. This relationship, known as a trophic cascade, demonstrates how the choices of a single predator reverberate through multiple layers of the ecosystem. The history of this cascade is written in the rise and fall of kelp forests over the past centuries. Before widespread human activity, sea otters thrived along the Pacific Rim, from Japan to Alaska to California. Their presence kept urchin populations in check, and kelp forests flourished. Then came the fur trade. Sea otters were hunted with devastating efficiency, valued for their thick pelts. By the late 19th century, otter populations collapsed across much of their range, leaving entire coastlines without their keystone predator. The result was immediate and catastrophic. In places like British Columbia, California, and the Aleutian Islands, urchin numbers surged. With no otters to restrain them, the urchins expanded into dense carpets along the sea floor. Kelp holdfasts were devoured, blades severed, and forests uprooted. What had once been vibrant underwater jungles transformed into urchin barrens, expanses of bare rock populated almost exclusively by urchins, devoid of the complex structure that once sustained thousands of species. In the absence of kelp, coastal productivity collapsed. Fish populations dwindled without nursery habitat. Crabs and abalone declined sharply. Seabirds that relied on fish feeding grounds experienced reduced nesting success. Even commercially important fisheries suffered, because many species that humans depend on begin their lives in kelp forest nurseries. The ripple effects extended far beyond the immediate predator-prey dynamic. It was an ecosystem unraveling in slow motion, and at its center was the absence of a single hunter. One of the most striking examples occurred in the Aleutian Islands, where the removal of sea otters triggered a chain reaction involving not only urchins, but kelp, fish, eagles, and even oceanic conditions. As kelp forests disappeared, urchins expanded through every rocky habitat. Fish species declined, and bald eagles shifted their diet from fish to seabirds. Meanwhile, the absence of kelp allowed stronger waves to strike unprotected coastlines, increasing erosion. What began as hunting pressure on otters ended as a transformation of the physical and biological landscape. But the reverse is equally true. When sea otters were reintroduced or naturally recolonized parts of their former range, kelp forests rebounded. In Monterey Bay, California, otters reclaimed territories abandoned for decades. Within a few years, kelp forests regenerated, bringing back the complex food webs that depended on them. The transformation is so rapid and dramatic that scientists have used kelp forest recovery as a model for ecosystem restoration worldwide. It is a vivid demonstration that some of the ocean's most important alliances are invisible until they break. Sea otters continue to play this guardian role in the present day. As they forage, they constantly adjust their diving routes and hunting habits. Their high metabolic needs drive them to explore every corner of the kelp forest, distributing predation pressure evenly across urchin populations. This spatial consistency prevents urchins from congregating in safe pockets and overwhelming localized regions of kelp. Otters do not allow urchins to hide behind boulders or cling to cliffs. Their pointed snouts and dexterous paws reach into crevices that most predators cannot access. Their influence also extends to carbon dynamics. Kelp forests store large amounts of carbon through rapid growth and burial of dead biomass. When kelp forests flourish under otter protection, their carbon sequestration increases significantly. In regions with strong otter populations, kelp forests absorb far more carbon than their unprotected counterparts. Thus, through their feeding behavior, sea otters become inadvertent allies in mitigating climate-related impacts. Other species benefit as well. When kelp forests grow dense, they reduce wave energy reaching the coast. This softens the impact of storms, protects shorelines from erosion, and stabilizes sediment. Tide pools, estuaries, and shallow water communities flourish as a result. The presence of otters upstream in the food web produces impacts downstream, impacts that reshape the physical environment itself. Despite their ecological importance, sea otters face ongoing threats. Oil spills mat their fur, stripping them of insulation. Pollution affects their prey. Climate shifts alter the distribution of kelp and urchins alike, and in some regions, competition with fisheries creates tension, as sea otters consume shellfish species valuable to humans. When these pressures reduce otter populations, kelp forests begin to show early signs of decline. Thinning canopies, reduced biodiversity, increased urchin cover. The system holds for a time, but without sustained otter presence, it slowly unravels. In the water column beneath the kelp canopy, the interconnectedness of the system becomes visible. Schools of juvenile fish hide within the shadows, clustering near the blades for safety. Crabs weave between the stipes, navigating a maze that protects them from predators. Snails graze quietly on the algal film that grows over the plants. Even sea lions and seals swim through the forest, using the thick kelp to evade sharks. Every motion, every interaction, every moment of survival depends on the structure the kelp provides. Structure that exists only because sea otters keep urchin numbers balanced. As the tide rises and the kelp canopy begins to lift with the changing water level, a sea otter floats near the edge of the forest. It cracks open another urchin on its chest, unconcerned with the ecological weight of its meal. Around it, the kelp sways in the rhythm of the surf. Fish move in coordinated flickers. Invertebrates cling to blades that would not exist without the otter's persistent, daily foraging. The guardian of this underwater world is not a giant or a hunter of impressive strength. It is a small, buoyant mammal whose appetite shapes coastlines. And in its simple, constant act of eating urchins, it maintains the survival of thousands of species, proving that some of the most powerful alliances in nature are not cooperative at all, but the quiet balancing acts of predators who never know the full magnitude of their influence. The morning tide drifts gently across a shallow lagoon, the water so clear that sunlight reaches the bottom in shimmering, wavering bands. Beneath the rippled surface lies a landscape that resembles an underwater meadow. Long blades of seagrass stretching outward in thousands of swaying rows, forming one of the most productive ecosystems on Earth. Tiny bubbles of oxygen cling to the blades. Clouds of juvenile fish scatter among the green corridors. Crabs shuffle in the soft sediment, while snails graze quietly. This is no passive underwater garden. It is a living city of photosynthesis, nutrient exchange, and constant movement. And at the heart of this city, shaping its structure and vitality with every bite, is the green sea turtle, the ocean's quiet, ancient gardener. The green sea turtle does not cut seagrass out of instinct alone. It shapes entire meadows through its grazing. As the turtle glides across the meadow floor, the rhythm of its flippers sends faint spirals of sand drifting upward. It lowers its head and bites cleanly through a patch of seagrass, cropping it to a consistent height. Then it moves on, feeding slowly but steadily, leaving behind a trimmed zone that looks remarkably like a freshly mowed field. This grazing does not harm the seagrass. It invigorates it. Young shoots grow thicker, more nutrient-rich, and more productive after being cut. The trimming stimulates new growth, the way pruning stimulates fruit trees or fire stimulates certain grasslands on land. The turtle, without knowing it, performs the same ecological service as a terrestrial herbivore, maintaining the structure, health, and productivity of the biome it depends on. Every bite a green turtle takes influences the flow of energy through the meadow. Long, uncut seagrass becomes tough, fibrous, and lower in nutritional value. It accumulates dead tissue that shades growing blades and reduces photosynthetic efficiency. Left unchecked, the meadow can choke itself, accumulating so much biomass that it begins to rot from the bottom upward. But where turtles graze consistently, the seagrass remains short, tender, and beautifully productive. These cropped zones support higher oxygen release, faster nutrient turnover, and more vigorous vertical growth. Fish, crustaceans, and invertebrates favor these trimmed patches because they offer better shelter and a richer variety of food sources. In this way, the green turtle becomes a keystone gardener. Its appetite prevents stagnation, its movement redistributes nutrients, and its presence increases biodiversity. Tracking studies over the past decades reveal something remarkable. Green sea turtles do not graze randomly. They return to the same feeding plots repeatedly, revisiting specific patches year after year, like farmers tending familiar fields. Satellite tags show turtles swimming entire kilometers to reach particular plots with preferred seagrass species, then spending hours in those zones before moving on. Some of these feeding grounds persist through multiple generations of turtles, suggesting a cultural component embedded within migratory routes. A turtle that hatches in a distant nesting beach may grow for years in open ocean, only to eventually return to the coastal shallows where it first imprinted on the chemical signature of its natal region. Once settled, it adopts a home range within the meadow and maintains it like a dedicated steward. This focus on specific plots means that turtle grazing pressure is not evenly distributed. Some patches experience heavy trimming, while others grow tall and untouched. These variations create a mosaic of microhabitats, each with its own structure and community. Short grazed areas house agile schooling fish and smaller predatory species that rely on open visibility and maneuverable space. Taller patches harbor camouflaged creatures like pipefish, decorative shrimp, and juvenile cephalopods that hide among the dense blades. The combination of grazed and ungrazed zones produces a spatial complexity that enriches the meadow's biodiversity. Without turtles, this mosaic collapses. The habitat becomes either overly dense or barren, depending on environmental pressures. The green sea turtle's alliance with seagrass meadows is one of nature's most elegant examples of mutualistic balance. The turtle receives energy-rich food and safe resting areas within the gently swaying blades. In return, the meadow gains maintenance that stimulates growth, prevents overaccumulation, and supports the larger food web that depends on vibrant seagrass. It is a partnership built not on coordination or intention, but on ecological necessity. Each partner thrives when the other performs its natural role. The importance of this relationship becomes even clearer when viewed across long timescales. Historical accounts show that where turtles once flourished, seagrass meadows thrived as dense, productive habitats stretching across coastal shelves. When human exploitation intensified, particularly during centuries of hunting green turtles for their meat, shells, and oil, turtle populations plummeted. In many regions, their numbers dropped by more than 90%. In their absence, the seagrass ecosystems they shaped began to change. Without systematic grazing, the meadows grew unevenly. Some areas developed excessive biomass that decayed and depleted oxygen. Others became vulnerable to disease and algal overgrowth. Biodiversity declined as certain fish species lost nursery habitats or feeding grounds optimized by turtle activity. The loss of turtles also influenced nutrient cycling. When turtles graze, they stimulate seagrass to uptake more nutrients from sediment and water. The trimmed blades increase carbon assimilation rates, strengthening the meadow's role as a carbon sink. Seagrass meadows are among the most effective carbon-sequestering ecosystems on Earth, storing large amounts of carbon in their roots and sediments. When grazing declines, this sequestration efficiency falls. Meadows become less productive, fewer nutrients flow through the food web, and local fisheries suffer. What appears to be a simple herbivory relationship is, in truth, a pillar of coastal productivity. The ecological consequences of turtle decline have been documented most dramatically in regions where seagrass meadows collapsed entirely. In parts of the Caribbean, where green sea turtle populations were reduced to a fraction of their original numbers. Some seagrass beds became overgrown and vulnerable to die-offs triggered by storms, heat stress, or disease. Without turtles to clip the seagrass and stimulate regrowth, the meadow's resilience weakened. Attempts to restore these meadows through human intervention revealed what was missing: the continuous, daily trimming of a roaming herbivore capable of covering wide stretches of habitat. No machine or conservation technique could replicate the subtle, dispersed, and persistent influence of the turtles' grazing. But where turtles have returned, often through conservation efforts or natural recolonization, seagrass ecosystems have recovered with surprising speed. In West Africa, Australia, Mexico, and parts of the United States, protected turtle populations have grown over the past few decades. As they recolonize former feeding grounds, researchers observe immediate signs of meadow revitalization: denser seagrass, greater species diversity, restored nursery habitats, and improved water clarity. The return of turtles initiates a positive feedback loop, where healthier seagrass supports more fish, which in turn supports predators and entire coastal food webs. This recovery reveals the depth of the green sea turtle's ecological importance. Its presence does not merely sustain seagrass, it stabilizes entire coastal systems that stretch from invertebrate communities to fish schools to apex predators. Even shorebirds, which hunt small creatures in the shallows, rely indirectly on turtle-maintained meadows. And humans too gain from the productivity of seagrass cities. Fisheries, tourism, shoreline protection, and carbon sequestration all benefit from the quiet work of the turtle mowing its underwater fields. Another intriguing element of turtle-seagrass interactions lies in nutrient redistribution. As turtles graze on different patches and move between resting and feeding grounds, they excrete partially digested plant material enriched with nutrients. This fertilizes the meadow, stimulating additional growth and increasing the rate of carbon and nitrogen cycling. It is a process analogous to grazing mammals on land that enhance grassland fertility through dung. The turtle's movement ensures that nutrients are not locked in one location, but spread across the seagrass landscape. Furthermore, the physical act of grazing shapes sediment dynamics. When a turtle uproots small shoots or disturbs sediment while feeding, it increases bioturbation, the mixing of sediment layers. This mixing oxygenates the substrate, reduces harmful buildup of sulfides, and supports beneficial microbial communities that enhance seagrass health. In this sense, turtles perform the combined roles of gardener, fertilizer distributor, and soil aerator, all within the soft sediments of shallow marine habitats. Even the turtle's behavior as it rests among the seagrass has ecological consequences. The weight of a resting turtle can bend the blades, increasing light penetration to lower layers. Its movements create small clearings where juvenile fish can gather. Predators learn to patrol the edges of these clearings, generating micro-habitats defined by the turtle's presence. These subtle interactions shape the social and spatial structure of the meadow community. As the sun climbs higher, warming the shallows, a green sea turtle glides slowly through a familiar patch of short-cropped seagrass. Its path is not random. It moves directly toward the same feeding lane it grazed the day before, and likely the day before that. It clips a few blades, rises for air, then descends again, repeating the cycle with consistency that borders on ritual. Around it, thousands of creatures move through the meadow it helps maintain. Juvenile fish dart through the cropped grass. Crabs sift through sediment loosened by the turtle's passage. Snails graze on the growing algae that flourish on the fresh young seagrass. This, ultimately, is the essence of the alliance. The turtle gains food, protection, and stability from the meadow, while the meadow gains maintenance, resilience, and life from the turtle. It is a partnership without coordination or conscious agreement, built entirely on ecological process. Yet it is one of the most important relationships in coastal marine ecosystems. A reminder that some of the ocean's most powerful alliances are not loud or violent, but quiet acts repeated over centuries. As the tide rises and the meadow begins to sway more vigorously in the current, the green sea turtle lifts its head toward the surface, inhales, and sinks deeper into the green world it has shaped. Through every bite, every movement, every return to its chosen feeding plots, it maintains the seagrass cities that shelter thousands of lives. A gardener by necessity, a keystone by accident, the turtle preserves the underwater fields that anchor entire coastal ecosystems. In the quiet margins of a tropical reef, Where sunlight fractures into shifting mosaics of gold and turquoise, the sand looks deceptively still. Small ripples trail across it in delicate patterns carved by currents, grazing fish, and the slow drift of the tide. But beneath this calm surface lies one of the most sophisticated pieces of biological engineering in the marine world. A burrow system built, maintained, and defended by a creature that is equal parts architect and weapon. The mantis shrimp, compact but powerful, moves grains of sand and fragments of shell with the slow precision of a construction worker. It digs, compacts, reinforces, and remodels its burrow over days, weeks, and years. Nearby, a small goby hovers outside the entrance, scanning the water column with quick, nervous flicks of its tail. Together, these two animals form one of the ocean's most remarkable and unlikely alliances, a blind engineer and a vigilant lookout, bound by a mutual survival pact that has persisted for millions of years. The mantis shrimp's burrow begins as a simple depression in the sediment. Using its specialized raptorial appendages, limbs powerful enough to crack mollusk shells or strike with the speed of a bullet, it scoops sand from the seabed and tosses it aside. But this is only the first step. The shrimp shapes the tunnel with meticulous care. It lines the walls with compacted sediment and reinforces them with small stones and fragments of coral rubble. Some species even incorporate plant fibers or shell shards for stability, creating a structure that can withstand wave surges, predator attacks, and seasonal shifts in sediment flow. Over time, the burrow becomes a multi-chambered refuge, a resting chamber, a storage area, a hidden entrance, and a main entrance that opens onto the sandy field outside. This architectural feat is more than a shelter. It is the heart of the mantis shrimp's life. From within its reinforced walls, the shrimp ambushes prey, evades predators, and raises young. But the shrimp faces one major limitation. It sees extremely well at close range, but poorly at distance when buried in the sediment. Although mantis shrimp possess some of the most sophisticated eyes on Earth, capable of detecting polarized light, ultraviolet wavelengths, and minute color variations, their visual brilliance works best in open visibility. Inside a tunnel, peering through a narrow entrance, the shrimp becomes nearly blind to threats approaching from afar. This is where the goby enters the story, a fish far less powerful, but far more perceptive in the open water column. Perched just above the burrow's entrance, the goby hovers like a sentinel. Its eyes scan constantly for movement, the drifting silhouette of a predatory fish, the shadow of an octopus, the subtle shift of a crab creeping too close. Gobies possess fast response times and strong anti-predator instincts. But alone in the open, the goby is highly vulnerable. Without a shelter, it becomes easy prey for countless reef hunters. The burrow offers safety, a refuge deeper and more secure than any rock crevice. The goby gains a home, and in return, it lends the mantis shrimp the one thing the shrimp cannot reliably provide for itself: early detection of danger. The communication between shrimp and goby is beautifully understated. The goby maintains physical contact with the shrimp's antennae or body, sometimes resting on top of the shrimp or brushing lightly against it. This tactile link acts as a real-time warning system. When the goby senses danger, it signals with a rapid flick of its tail or a sudden, rigid posture. The shrimp responds immediately, retreating deeper into the burrow. In some species, the shrimp will even place its antennae outside the sand to maintain contact with the goby during small adjustments of the entrance. This constant exchange transforms the burrow from a simple shelter into a shared command center, where two very different species maintain synchronized vigilance. Together, the pair forms a living organism more capable than either member alone. The goby gains a fortress, the mantis shrimp gains eyes. The alliance is not born from friendliness, but from evolutionary pragmatism. For millions of years, such partnerships have allowed mantis shrimps and gobies to thrive in zones that would otherwise be too dangerous or unstable. Fossil and genetic evidence suggests that this relationship predates many modern reef fish lineages, implying that early versions of this partnership emerged long before the reefs we know today reached their current complexity. From an ecological perspective, the burrow acts as a micro-habitat. As the shrimp excavates and maintains its tunnel, it aerates the sediment, increases mixing between oxygen-rich surface layers and deeper layers, and stabilizes the substrate against erosion. These changes improve local sediment chemistry, influencing the microfauna that live within the seabed. Small worms, microbes and crustaceans benefit from the improved oxygen flow and the structural pockets created by burrow maintenance. In a sense, the mantis shrimp does not merely build a home, it engineers a tiny ecosystem. As the shrimp expands its burrow, the goby remains ever watchful. It hovers within a narrow range, never straying far from the entrance. When a threat passes, perhaps a predatory jack or a cruising barracuda, the goby sends another subtle signal. The shrimp, sensing through touch as much as vision, emerges again to continue construction or wait for prey. This cyclical pattern of labor, vigilance, retreat, and re-emergence becomes the rhythm of their shared life. During feeding times, the mantis shrimp uses its extraordinary strike to capture prey. Depending on the species, the shrimp may be a smasher, delivering blows powerful enough to break shells, or a spearer, striking soft-bodied prey with barbed appendages. Both hunting styles rely on precision and speed. The shrimp's strike is among the fastest movements in the animal kingdom, accelerating with the same force found in rifle bullets. But these attacks require the shrimp to position itself partly outside the burrow, exposing it to danger. Here again, the goby's presence becomes essential. With a lookout stationed above, the shrimp can hunt more confidently and aggressively, knowing that any approaching threat will be detected early. The efficiency of this partnership increases survival rates dramatically for both species. Gobies that live with mantis shrimps suffer fewer predation losses than those living independently. Shrimp that maintain gobies experience reduced threat exposure and can devote more time to burrow maintenance, reproduction, and hunting. Studies show that shrimp-goby pairs survive longer and reproduce more successfully than solitary individuals. The mutual benefits are so significant that natural selection has reinforced this relationship across multiple mantis shrimp and goby species throughout the Indo-Pacific region. The partnership is finely tuned, sustained through constant behavioral negotiation. Gobies rarely enter the burrow fully, preferring to hover or perch near the entrance to maintain a wide field of view. Shrimp rarely venture far outside the opening unless the goby is present. When the shrimp blocks the entrance during dangerous periods, using its own body or plugging the hole with sediment, the goby retreats inside until the threat passes. When the shrimp reopens the entrance, the goby resumes its sentry position as though nothing has happened. The smoothness of these transitions suggests deeply ingrained instinctive coordination. Even during burrow cleaning, the roles remain complementary. The shrimp often excavates sand and debris from within, pushing it outward through the entrance. The goby positions itself just above the plume of particles, helping to disperse the sediment with fin movements that reduce buildup around the opening. This seemingly small behavior keeps the entrance clear, preventing the burrow from collapsing or becoming clogged, an important advantage in dynamic environments where currents deposit shifting layers of sand. The partnership influences their reproductive behavior as well. Some goby species lay eggs within the burrow, using the structure built by the shrimp as both a nursery and a refuge. The presence of the goby ensures that predators searching for eggs or larvae encounter a vigilant adult before reaching the nest. The shrimp, in turn, gains additional motivation to maintain the burrow's integrity during these periods, expanding and reinforcing the structure to accommodate both species safely. In broader ecological terms, the mantis shrimp-goby alliance contributes to the health of sandy reef zones. These zones, often overlooked compared to coral or mangrove habitats, play essential roles in nutrient cycling and species diversity. The presence of burrow systems increases habitat complexity, providing shelter for countless microfauna and influencing sediment patterns over wide areas. The goby's constant patrolling deters small predators and regulates movements of invertebrates that might otherwise overgraze microalgal mats. Together, the pair functions as a stabilizing force within the sandy flats. The evolutionary logic behind this alliance resembles a long-term roommate agreement refined over unfathomable stretches of geological time. One partner builds and maintains the home, the other guards the door. One possesses the tools of a master engineer, the other carries the awareness of a watchful sentinel. Their lives intertwine not through affection, but through necessity and efficiency. It is an arrangement so successful that natural selection has preserved it through shifting climates, changing sea levels, and mass ecological transformations. As afternoon light slants across the reef and the tide shifts, the mantis shrimp withdraws slightly into its burrow while the goby continues to hover, its fins trembling in the currents. The two creatures share a connection that exists beyond words, beyond intention, beyond conscious understanding. It is a partnership rooted in instinct and reinforced by survival, a design perfected over millions of years. Inside the quiet burrow, the shrimp rests in the architecture it has built. Outside, the goby watches with vigilance that never wavers. Together, they form a single unit, an engineer and its lookout, shaping the world beneath the sand grain by grain. In the flickering half-light of a coral reef, where beams of sun break into shifting ribbons of blue and gold, a slender form glides through the water with the quiet assurance of a creature evolved for precision. Its movement is neither serpentine nor fish-like, but something between. A smooth, effortless ribbon of muscle that bends and flows through tight spaces as though water yields before it. This is the sea snake, a reptile so perfectly adapted to the reef that it navigates cracks, ledges, and coral labyrinths with a fluidity no fish can match. While sharks dominate open water and groupers command broad territories, the sea snake rules the spaces in between, slipping through the reef's hidden arteries to reach prey that others cannot touch. Sea snakes are among the most specialized predators in the tropical ocean. Their flattened tails act as natural paddles, propelling them forward with gentle sculling strokes. Their lungs stretch nearly the length of their body, allowing them to store enough air for extended dives. Some species even absorb part of their oxygen supply through their skin, a remarkable adaptation for a reptile that evolved from land-dwelling ancestors. Their senses are tuned to detect faint vibrations and chemical cues that lead them toward hidden prey. And their venom, designed for rapid immobilization, allows them to subdue slippery fish with minimal struggle. But their hunting method is what makes them truly unique. Sea snakes do not stalk the open reef. They invade the crevices that form the reef's foundation. They enter holes, tunnels, and cracks that most predators cannot reach, rooting out the small fish and eels that hide in the reef's understructure. In doing so, sea snakes become unintentional catalysts for one of the reef's most dynamic predator interactions. When a sea snake threads its way into a crevice, the small fish hiding inside face a terrifying dilemma. Stay in the hole and risk being caught by the snake's narrow jaws, or flee into open water, where larger predators roam. Many choose flight. They erupt from the hole in sudden bursts, scattering into the water column in chaotic flashes of silver, and waiting nearby, often already tracking the snake's movements, are groupers, jacks, trevallies, and other opportunistic predators. For these hunters, the sea snake becomes a moving tool, flushing out prey that would otherwise remain hidden. This flushing effect turns a solitary predator into a mobile disturbance that reshapes feeding opportunities for multiple species. Groupers, with their broad bodies and powerful jaws, lack the ability to enter tight crevices. Sharks, even the smaller reef species, rely on open water pursuit. But when a sea snake pushes into a hole, these limitations vanish. Prey that once lived beyond reach suddenly spills into their hunting zone. The alliance is unspoken and unintentional, a byproduct of overlapping goals. The snake hunts for itself, yet its actions benefit others. The larger predators follow, not out of cooperation, but because the snake's movements shift the structure of the reef community every time it enters a fissure. Some predators appear to anticipate sea snake movements. Divers have recorded groupers trailing behind snakes like shadows, positioning themselves precisely at the crevice exits. As the snake advances, the grouper waits in stillness, its broad pectoral fins fluttering gently to maintain position. The moment prey darts outward, The grouper lunges with startling speed, creating a sudden vacuum of water that pulls the fleeing fish directly into its mouth. The snake, still focused on the prey inside the tunnel, continues its hunt unaffected. It does not react to the commotion behind it. It does not signal the grouper, nor does it gain from the grouper's catch. But the grouper gains immensely, sometimes doubling its feeding success simply by following a snake's route. Sharks also take advantage of these moments. Though they lack the fine maneuverability needed to track snakes through tight corals, they linger at the edges of the reef slope. When a sea snake moves through a particularly dense crevice system, multiple prey species may flush out at once, forming small clusters of panicked fish. Reef sharks, patrolling with calm persistence, use these events to strike with surgical precision. The synergy between snake and shark remains loose. No communication, no mutual recognition. But the combined effect increases the efficiency of both predators. The snake extracts prey from the reef's interior. The shark reaps the benefits from the sudden release of vulnerable fish into open water. Even mid-level predators participate. Trevallies, snappers, and barracudas all respond to the snake's disturbance, each using their specific hunting strategies. Trevallies rely on bursts of speed and sharp turns. Snappers strike at medium range with explosive lunges. Barracudas wait at the periphery, using their ambush style to target fish straying too far from the safety of the reef. In these moments, the reef becomes a shifting battlefield of cascading responses. The snake's exploration triggers prey flight, which triggers predatory lunges, which ripple through the surrounding community in seconds. But the most surprising beneficiaries of the sea snake's presence are not the large hunters. They are the small thieves. Certain reef fish, such as wrasses, groupers in juvenile stages, and even some damselfish, learn to follow sea snakes closely, sometimes swimming inches from the predator's coils. They are not joining the hunt. They are searching for leftovers. When the snake captures a fish inside a crevice, small pieces of tissue may drift outward. Some prey attempt partial escape and succumb near the entrance. Others injure themselves during the chase. These scraps feed an entire micro-ecosystem of opportunistic species. This feeding strategy requires calculated risk. The snake is dangerous. Its venom can immobilize fish in seconds. But the small shadowing fish use their agility and size to remain outside strike range. They dart in quickly, grab any available scrap, and retreat before the snake's hunting reflex activates. These fish view the sea snake the way scavenger birds view large predators on land, as a source of opportunity, not cooperation. The snake does not benefit from their presence, but it also does not lose energy attempting to deter them. Its focus remains deep inside the reef structure, where its slender head searches for prey hidden in darkness. Sea snakes hunting in coral labyrinths create ecological benefits even beyond predator feeding opportunities. By removing fish and eels that hide deep within the reef, they alter the competitive balance among species. Some small reef fish specialize in occupying specific holes, relying on structural complexity to avoid predation. When sea snakes reduce their numbers, other species expand their territories. This redistribution affects grazing pressure on microalgae, changing how the reef surface develops and which algae dominate. It influences where invertebrates settle, altering the growth patterns of sponges, ascidians, and coral recruits. In essence, the sea snake acts as a regulator of the reef's inner spaces, shaping microstructure through predation. Their presence also affects nocturnal dynamics. Many sea snakes are active during daylight hours, but some species continue hunting into dusk. The twilight zone of the reef, that narrow window when day-active species retreat and night-active species emerge, becomes especially chaotic when snakes are hunting. Prey moving from daytime hiding spots to nighttime feeding areas must navigate both the snake's crevice hunting and the open water predators that begin their nightly patrols. This intersection of predator strategies increases turnover in prey populations, redistributing energy through the reef community. Sea snakes themselves face predation from a few species, though these interactions are relatively rare. Large sharks occasionally attack them. Sea eagles may snatch them during surface ascents, but generally, sea snakes occupy a stable niche with few direct competitors. Their venom gives them advantages in tight spaces where larger predators cannot maneuver. Their body shape allows access to microhabitats too small for most fish. Their hunting strategy reduces competition and creates cascading feeding opportunities for others. This makes them one of the reef's most influential, yet least conspicuous controllers. They do not dominate through power, but through mobility. They do not coordinate hunts with other species, but trigger feeding events that shape predator-prey interactions. They do not intend to help other animals, but their presence affects who eats, who flees, and who survives. The ecological ripple effects become clearer when sea snake numbers fluctuate. In areas where sea snake populations have declined due to fishing bycatch, pollution, or habitat loss, studies report changes in reef fish distribution. Eel populations grow in the absence of snake predation, altering competition within crevices. Some small fish species become more abundant, others decline due to increased competition. The balance of species occupying the reef's interior shifts, influencing grazing patterns, detritus flow, and coral settlement. In systems shaped by crevice complexity, the snake's absence rewires community organization, proving that even without forging intentional alliances, sea snakes shape their ecosystems with surprising reach. As afternoon sunlight softens into amber tones, a sea snake glides along a coral wall. Its tongue flicks gently, tasting chemical cues in the water. It dips into a narrow slit between two coral heads, its body disappearing inch by inch. A small cloud of disturbed sediment rises. Within moments, a school of tiny fish bursts from another exit, scattering in a flurry of movement. A grouper, waiting with absolute stillness, snaps up two of them. A trevally intercepts another. Meanwhile, three small wrasses dart in to investigate crumbs drifting from the crevice. The snake emerges again, undisturbed, already sliding toward its next hunting tunnel. It has no concept of the chaos it creates in its wake. It hunts only for itself, but the entire reef responds to its presence. It is a controller without intention, a catalyst without planning, a predator whose movements dictate moments of opportunity and risk for countless others. In the crowded, competitive world of the coral reef, the sea snake does not simply belong. It shapes the system. And in the spaces where coral branches tighten, where light fades and cracks wind into the reef's hidden depths, the snake remains unmatched, a silent ruler of the narrow places, guiding who eats, who escapes, and how life flows through one of the richest ecosystems on Earth. In the dim blue quiet of a sandy seafloor, where the reef's bright colors fade into a muted landscape of rippled sediment, a solitary male pufferfish begins his work. The tides have deposited a fresh layer of fine sand across the flats, smoothing the terrain into a blank canvas. Most creatures drifting past see nothing remarkable here. No shelter, no rocky outcrop, no patch of algae, nothing to suggest purpose. But the pufferfish sees potential. With the faintest twitch of his fins, he hovers above the sand, tracing an invisible boundary. Then, in a motion repeated countless times across evolutionary history, he begins to carve a masterpiece. A vast, geometric sand circle, unlike anything else in the natural world. Slowly, hour after hour, the small fish plows through the sand with rhythmic beats of his fins. He pushes sediment aside, sculpting furrows that radiate outward in perfect symmetry. His movements are not frantic or random. They follow an ingrained pattern of instinctual precision. He alternates between sweeping gestures that form wide valleys and delicate adjustments that create narrow ridges. The structure expands into a circular mandala, sometimes more than a meter across, many times larger than the artist himself. Viewed from above, it resembles a sunburst, a star, or a multi-tiered flower carved into the seafloor with breathtaking mathematical accuracy. This behavior, discovered only in recent decades, stunned scientists. Here was a tiny pufferfish constructing a complex architectural design with purpose and consistency, a display of craftsmanship that rivals the courtship dances of birds or the intricate nests of bowerbirds. But for the pufferfish, the structure is more than art. It is a direct expression of genetic quality, a communication system written not in sound or color, but in architecture. The male's ability to create a precise sand circle, The symmetry, the stability, the complexity of patterns signals to females that he is healthy, coordinated, and strong. In a world where survival demands precision, such traits matter profoundly. Yet the sand circle is not merely a signal. It becomes, unintentionally, a micro-habitat. As the pufferfish sculpts ridges and depressions, he alters the flow of water across the seafloor. Tiny currents deflect around the raised valleys. Fine sediments settle in the innermost depressions. Water slows in some pockets and accelerates in others. These hydrodynamic changes create gradients of oxygen, temperature, and particle distribution that attract small invertebrates. Crustacean larvae, planktonic worms, juvenile mollusks, and microscopic organisms drift into the circle, settling into the patterned grooves where calmer water offers refuge from predators and currents. Thus, a mating display inadvertently becomes engineering. The pufferfish designs for attraction, but the ecosystem reads a different opportunity. The valleys provide shelter for tiny creatures. The peaks interrupt water flow, increasing sediment heterogeneity. Invertebrates that might otherwise be swept away by steady currents find the circle's interior a safe haven. Over the days, the male maintains his creation. A small colony of life emerges within the structure, a micro-ecosystem born from the architectural demands of courtship. The construction process is meticulous. Each ridge must be precisely angled, or it collapses under shifting sand. Each valley must be deep enough to hold its structure, yet shallow enough not to crumble. The pufferfish performs constant maintenance, revisiting sections that deform due to tidal changes or passing animals. He reinforces ridges with sand from the outer zone. He smooths the central court, the innermost flat region of the circle, where he will eventually present himself to potential mates. He trims and reshapes until the structure achieves rotational symmetry, a design that echoes natural fractals in coral growth or the radial patterns of flowers. But unlike those examples, the pufferfish's creation is purposeful, deliberate, and executed entirely by a single animal, using only fins and instinct. Females approach cautiously. Their eyes register subtle asymmetries invisible to most observers. They assess ridge height, spacing precision, and the stability of the pattern as currents pass over it. These details reveal everything they need to know about the male's energy reserves, motor control, and resilience. A poorly sculpted circle suggests weakness or inexperience. A collapsed ridge signals a male unable to fend off environmental disturbances. A perfectly carved pattern, however, communicates a lineage strong enough to survive in shifting sands, storms, and predation. When the female enters the circle, the male performs a final display. He stirs fine sand from a central depression into the water, creating a shimmering cloud that settles into the innermost basin. This material becomes the substrate on which the female lays her eggs. The center of the circle is designed not for aesthetics, but for function. A small, protected zone where eggs attach securely to fine grains rather than coarse rubble. This detail reinforces the precision of the structure. The art is not mere decoration. It shapes hydrology in a way that enhances egg survival. Once the eggs are laid, the female departs. The male remains behind, guarding the central basin and continuing to maintain the structure. As currents shift and predators approach, he protects the developing brood. He also preserves the outer ridges, smoothing disrupted sections and reinforcing weak points. Even if the female has left, the structure still matters. It influences water flow and sedimentation around the eggs, protecting them from being buried or exposed. The male's architectural skill becomes a shield against environmental unpredictability. During this period, invertebrates continue colonizing the sand circle. Some benefit directly from the male's maintenance. If he displaces sediment while defending the eggs, fresh fine grains settle into the ridges, creating new niches. If he smooths the central basin, a small flurry of particles drifts outward, attracting opportunistic scavengers that feed on the organisms stirred from the sediment. In this way, the circle transforms from a simple courtship platform into a dynamic habitat shaped by the interplay of design and survival. The emergent alliance is subtle but profound. The pufferfish gains a mate and increases his reproductive success through architecture that communicates his fitness. The invertebrates gain a sculpted shelter created incidentally by the same architecture. They do not thank the fish does not recognize their presence. Yet the connection binds them. The biological structure designed for one purpose creates ecological benefits for many species. It is a quiet testament to how behaviors shaped by sexual selection can spill outward into ecosystem engineering. In this sense, the pufferfish becomes both artist and accidental habitat architect. Over evolutionary time, this behavior likely became more refined as females rewarded intricate patterns with higher mating success. Males with better spatial control, more symmetrical circles, and stronger endurance passed their traits to offspring. This drove the refinement of courtship architecture until it reached a level of complexity unmatched by most marine fish. The circles became not simply nests, but evolutionary advertisements, shaped by millions of years of pressure. Every ridge tells a story of ancestral males who survived predators long enough to sculpt circles just stable enough to impress females. These displays also highlight the role of environment as co-designer. The sand particles, grain size, current direction, and tidal cycle influence the final structure. A male pufferfish must adjust continuously. A slight shift in current requires recalculating ridge angles. A sudden surge of water may deform half the circle. A passing animal may erase an entire section. The male must not only build but problem solve, responding to unpredictable disturbances with adaptive corrections. This capacity for iterative refinement is part of what females evaluate. It is not the initial design alone, but the maintenance under pressure that signals deep genetic quality. By the time the eggs hatch, the circle may be partially degraded. The ridges may slump, valleys may fill with drifting sediment, and invertebrates may multiply in the temporary shelter. The male then abandons the structure, leaving behind a fading mandala that slowly erodes back into the landscape. Currents reclaim the sand. Blades soften. The microhabitat disperses. But the impact lingers. For a few days or weeks, a simple courtship ritual created an entire engineered habitat, influencing hydrodynamics, shelter availability, and biodiversity at a microscale. Over countless generations, these cycles of creation and dissolution have shaped sandy ecosystems in subtle ways. In areas with high pufferfish densities, the repeated construction of sand circles increases sediment turnover, oxygenating the upper layers and preventing anaerobic decay. Where circles cluster, invertebrate richness temporarily spikes, attracting small predators that feed on larvae settling in the grooves. Even seabed microorganisms respond, colonizing the finely sculpted sediments and altering nutrient cycles. Thus, the pufferfish's art, though ephemeral, forms part of the broader ecological rhythm of the seafloor. As the sun begins to set across the sandy plain, the male pufferfish performs his final inspections. He glides above the ridges, fin tips tracing the geometry he crafted with relentless dedication. Each groove softens in the evening light, glowing faintly as particles settle through the water column. Small invertebrates dart between the structures, unaware that their temporary home exists, because one small fish needed to impress a partner. In the end, the alliance that emerges is simple but profound. The fish gains a mate, the invertebrates gain a sculpted sanctuary, and the habitat gains a moment of engineered complexity born from the demands of sexual selection. The pufferfish, in carving beauty into the sand, becomes an artist whose work echoes quietly through the ecosystem, proving that even the smallest architects can shape the lives of many. Across the wide, shallow expanse of a tropical sand flat, the water glows pale turquoise under the rising sun. Soft ripples drift across the seafloor, carrying tiny particles that sparkle like suspended dust motes. To an untrained eye, the sandy bottom appears empty, a barren desert of fine sediment stretching outward in muted curves. But within this quiet landscape lies an ecosystem built on constant disturbance, shaped by creatures whose movements churn, sculpt, and renew the flat every day. Chief among these engineers is the stingray. Silent, broad-bodied, and deceptively gentle in its glide, The stingray acts as a living plow, reshaping the seabed with every dive it takes. The stingray's approach is nearly soundless. Its wings, technically modified pectoral fins, ripple with soft, wave-like undulations that lift it slightly above the sand. Its eyes scan the water column, while its mouth and sensory pores focus downward, reading the world hidden beneath the sediment. Stingrays carry one of the most finely tuned detection systems in the marine realm, arrays of electroreceptors that sense the faint electric fields produced by buried animals. Every worm twitch, every crab pulse, every heartbeat of a hidden mollusk emits a tiny signature. To the ray, the sand flat is not a blank sheet. It is a map rich with signals, each marking a potential meal. When the stingray detects buried prey, its body tenses for a moment. Then, with a sudden downward press of its wings, it sucks sediment upward in a violent rush. The peaceful flat explodes into motion. A crater forms instantly, swirling with clouds of beige, gold, and brown. The ray plunges its snout deep into the pit, hunting by touch and suction. Worms, clams, shrimp, and small fish hiding under the sand are exposed in seconds. The stingray feeds quickly, using its flattened teeth to crush shells and extract the nutritious flesh inside. As soon as the pit is cleared, the ray rises, gliding forward in search of the next signal. But in the wake of its foraging, something remarkable happens. A feeding event that lasts only moments for the ray becomes a bustling festival for dozens of other species. Within seconds of the first burst of sediment, small fish rush into the crater. Silversides, goatfish, wrasses, and even juvenile snappers stream into the murky plume. They dart through the cloud, snatching worms that escape the ray's grasp, or grabbing tiny crustaceans dislodged by the disturbance. The crater becomes a temporary market of opportunity, the kind of chaotic, unpredictable window that small fish rely on in the competitive flat. Crabs follow next. Blue crabs, ghost crabs, and small portunid species approach the pit cautiously, sensing the scent of freshly exposed food. They scrape through the sediment with their claws, digging out buried morsels the ray missed. Their movements create new micro-disturbances, triggering further releases of prey. Meanwhile, the very worms and shrimp the ray targeted attempt escape, only to be intercepted by tiny predators capitalizing on the confusion. Then, from the darker perimeter of the flat, larger shapes begin to appear. Small sharks, often juvenile blacktips, lemons, or reef sharks, drift into the zone, drawn by the scent plumes carried by the current. To them, a stingray excavation is an announcement. Something edible has been disturbed, and the scent signature reveals not only prey, but the digestive enzymes and body fluids that leak from partially eaten animals. The sharks do not threaten the ray directly. They focus instead on the scraps, injured creatures, or small fish fleeing the storm of activity. Thus, a single stingray's dive triggers a cascading multi-species response. What began as one animal's search for buried food becomes a temporary feeding hotspot, a short-lived explosion of biodiversity and competition that lasts until the pit fills again with settling sediment. This dynamic transforms stingrays into keystone disturbance generators. Each crater modifies the seafloor not just physically, but ecologically. The pits alter microtopography, creating depressions that fill with organic material as the water settles. These depressions attract detritivaries like small worms, amphipods, and scavenging crustaceans even long after the ray departs. As the pits gradually flatten over hours or days, they become nutrient-rich patches where microalgae and bacteria flourish, forming concentrated food sources for grazers. Over time, repeated stingray foraging creates a mosaic of microhabitats, some freshly excavated, some halfway filled, some fully smoothed, each offering a unique combination of resources. On a larger scale, stingray activity aerates the sediment. Buried layers, often low in oxygen, become exposed and oxygenated as the ray churns the upper layers. This mixing resets chemical gradients, increases microbial diversity, and prevents the buildup of harmful compounds like hydrogen sulfide. In this way, stingrays act as bioturbators, species whose movements enhance sediment health and productivity. Their engineering role extends beyond nutrient cycling. Many small fish species time their foraging to coincide with stingray activity. Goatfish, which use chin barbels to feel for prey, often shadow stingrays closely, taking advantage of exposed animals the moment the ray disturbs them. Wrasses form loose, shifting clouds around the ray's body, moving in and out like satellites. Some species have learned to anticipate stingray dives, reading subtle cues in the ray's posture or movement that signal an imminent excavation. Even small squid and cuttlefish occasionally sweep through the disturbed zone, grabbing crustaceans attempting to flee upward. The pit becomes a vortex of energy, a vertical plume of particles, a horizontal burst of scent, and a circular gathering of predators. All of this originates from the simple action of the stingray pressing its body toward the sand and inhaling a mouthful of sediment. As stingrays travel across the flat, they create a chain of craters, each becoming a momentary feeding arena. Over weeks, these disturbances form patterns that shape the distribution of organisms across the habitat. Areas frequently visited by rays host richer assemblages of scavengers. Sections with fewer disturbances accumulate deeper layers of undisturbed sediment, supporting different types of infauna. In this way, stingrays act as habitat architects on a broad spatial scale. Their impact is not intentional, yet it defines the ecology of sandflats worldwide. Some rays, such as southern stingrays in the Caribbean or blue-spotted ribbon-tail rays in the Indo-Pacific, engage in especially vigorous excavations. These species generate larger pits and create stronger sediment plumes. Their feeding events attract not only fish and small sharks, but sometimes even larger predators such as barracuda, which linger at the edges of the cloud waiting for startled prey to bolt outward. The cloud becomes a veil of confusion, reducing visibility for smaller prey species, but offering opportunities for fast, strike-oriented hunters. In seagrass meadows adjacent to sandy flats, stingrays play an additional role. As they dive into the sediment, they sometimes uproot seagrass shoots, leaving small gaps in the meadow. These gaps become settling zones for drifting seeds or spores. Some plants regenerate rapidly in these disturbed patches, increasing genetic diversity. Other organisms, like young fish and crustaceans, use these openings as temporary shelters. Thus, stingray foraging introduces variability into seagrass structure, variability that increases resilience over time. Historically, stingrays have been misunderstood as passive or even destructive. Early naturalists saw only the torn patches of seagrass or the churned sand left behind and assumed that rays damaged habitats. But long-term ecological research reveals the opposite. Rays maintain productivity, redistribute nutrients, and enhance opportunities for countless species. They act as the invisible plows that keep shallow ecosystems dynamic rather than static. Their disturbances mimic the effects of digging mammals on land, which create burrows that aerate soil and provide niches for smaller species. When stingray numbers decline due to fishing pressure, habitat destruction, or bycatch, the effects ripple outward. Sandflats become less aerated. Microbial communities shift toward lower oxygen tolerance. Small fish that depend on stingray disturbances struggle to find food. Predators lose the opportunistic bursts of feeding they once relied on. Even nutrient cycling slows, altering productivity across the entire flat. In ecosystems built on disturbance, removing the primary source of disturbance reshapes the structure of life from the bottom up. As the sun begins to descend toward the horizon, casting warm amber light across the shallow sea, a stingray glides once more across the flat. Its shadow moves smoothly over the sand, darkening the grains beneath. Then it pauses. Its body stiffens with purpose. Its wings drive downward in a sudden, decisive burst. Sediment erupts in a cloud as the crater forms instantly beneath the ray's body. Within seconds, the flat awakens. Fish rush in. Crabs scramble over the pit walls. A juvenile shark glides into the plume, searching for the first trace of movement. The stingray feeds silently at the center, indifferent to the swarm around it. For a brief moment, the entire flat revolves around a single excavation. This is the essence of the alliance. The stingray digs for itself. but every dive becomes a feast for the community. The flat survives and thrives because the ray plows its surface day after day, turning simple foraging into a cascade of opportunities. In the end, the stingray is not just a predator. It is a farmer, an engineer, and a quiet conductor of life across the shifting sands, feeding itself while feeding the entire ecosystem. At first glance, a starfish seems like the least likely creature to shape the destiny of a coral reef. It moves with a patience bordering on stillness, a drifting sculpture more than a predator. Its arms glide across the substrate with imperceptible speed, leaving no obvious disturbance beyond a faint ripple of tiny tube feet, gripping and releasing the rock beneath. Fish dart past it without a second thought, crabs step around it with casual indifference, and divers often swim over it without ever noticing it at all. Yet this quiet, slow-footed animal plays a role so foundational that entire reef communities hinge on its decisions. The starfish is the reef's slow-motion judge, an arbiter of space and growth whose feeding behavior determines which species rise to dominance and which remain suppressed. To understand its power, one must first appreciate that reefs are defined by competition. Space is the currency every organism covets, the limited two-dimensional platform on which corals, sponges, algae, tunicates, and mollusks attempt to anchor, grow, and expand. Unlike open water, where animals disperse freely, the reef concentrates life upon a fixed surface. Every square centimeter becomes a battleground. Sessile organisms, unable to move, invest in chemical warfare, rapid growth, or defensive skeletons. Faster-growing corals can overshadow slower ones. Invasive sponges can smother their competitors. Algae can carpet bare rock, preventing any coral settlement. Left unchecked, a single aggressive species could monopolize massive sections of reef, turning a diverse community into a monoculture. This is where starfish enter the story. By consuming specific prey, often selectively and rarely indiscriminately, they maintain balance. They prevent dominant coral species from overwhelming slower-growing varieties. They limit the spread of mussels and barnacles on rocky reefs. They nibble away at sponges that might otherwise multiply unchecked. Starfish are not simply predators. They are regulators of ecological opportunity. Their feeding creates openings for new corals to settle, for sponges to retreat into equilibrium, and for algae to be kept from suffocating the reef structure. Through slow-motion decisions, starfish maintain a living landscape that would otherwise collapse under the weight of competitive exclusion. Perhaps the most dramatic example of starfish influence is the crown-of-thorns starfish, a many-armed venom-spined species capable of devouring coral colonies with alarming efficiency. In normal numbers, crown-of-thorns starfish act like any other reef regulator. They feed selectively, often targeting fast-growing corals like acropora, preventing these species from blanketing entire reef slopes. They open space for slower-growing corals, enhancing diversity. But when something shifts within the system, excess nutrients, removal of key predators, changes in water quality, their populations can explode. During an outbreak, thousands of crown-of-thorns starfish descend upon a reef and strip it of living coral tissue. Entire landscapes are reduced to skeletal rubble, white and lifeless. These outbreaks are ecological alarms. They reveal how tightly balanced a reef must remain, how easily a chain reaction can push the system out of equilibrium. A natural population of these starfish maintains coral variety. An unnaturally large one destroys it. The lesson is subtle but profound. The same behavior that preserves diversity under stable conditions becomes catastrophic when amplified beyond ecological norms. It is not that starfish are villains during outbreaks. It is the system itself that has skewed the population dynamics. Overfishing removes predators such as giant tritons and specialized wrasses. Excess nutrients from land boost phytoplankton, which feed the starfish larvae, increasing survival rates. A reef that has lost its natural checks becomes vulnerable to runaway predation. Yet focusing only on the crown of thorns overlooks the quieter, more common role of starfish across global reefs. Many species, from blue Linkia starfish to mottled cushion stars, graze slowly across corals, algae, and invertebrates, acting as equalizers within the community. Some target sponges that threaten to overtake shaded reef crevices. Others feed on encrusting organisms that smother coral bases, preventing them from expanding. On rocky, temperate reefs, certain starfish species are the primary predators of mussel beds, ridding surfaces of dominant filter feeders, so barnacles, tunicates, red algae, and juvenile kelp can gain a foothold. Without these predators, a single mussel species could blanket entire boulder fields, rendering the community monotonous. The mechanism through which starfish feed is itself a quiet marvel of evolutionary engineering. Using hundreds of tiny suction cup tube feet, they grip the substrate with remarkable strength. Once they encounter suitable prey, a coral polyp, a mussel, or a sponge, they do not bite or tear. Instead, they pry the prey open with relentless patient pressure, sometimes for hours. Then, in one of the most unusual feeding strategies in the animal kingdom, they avert their stomach outward through their mouth, externalizing the organ and pressing it directly onto the prey. This stomach dissolves tissue with digestive enzymes, absorbing nutrients before being pulled back into the body. It is a slow, methodical process. But it is this very slowness that shapes the reef. A continuous, regulated pressure that prevents any one competitor from dominating. Starfish are also extraordinarily sensitive to environmental cues. Their tube feet detect chemical trails left by prey. Their bodies respond to the texture and composition of the substrate. Some species can even detect the presence of diseased or stressed corals, seeking them out as easier meals. This means that starfish contribute to natural turnover, removing weakened corals before pathogens spread widely. They perform a form of ecological sanitation, ensuring that energy flows from decaying or vulnerable organisms back into the food web rather than lingering in dying tissue that might attract parasitic infestations. The indirect alliances formed through starfish feeding are subtle but impactful. Small fish, such as damsels and wrasses, sometimes follow starfish to pick off creatures fleeing from the predator's path. Crabs lurk behind them, scavenging bits of tissue left after the starfish retracts its stomach. Snails and small worms colonize the freshly exposed surfaces of coral skeletons or rock where the starfish has grazed. The starfish does not intend to share its meals, but its feeding behavior creates a trail of secondary opportunities. In this sense, starfish act as silent facilitators of resource redistribution. What they consume is returned in fragments, nutrients, and open space that others can exploit. The most important function of starfish, however, remains spatial regulation. Conservation studies show that in areas where starfish are removed or their numbers drastically decline, certain corals begin to monopolize space. Their competitive edges expand unchecked. The reef becomes dominated by a handful of fast-growing species, and biodiversity drops sharply. What appears to be a vibrant coral forest becomes, on closer examination, an ecological monoculture. This reduced diversity makes the reef more vulnerable to bleaching, disease, and storm damage. Without a mosaic of coral species, each with distinct temperature tolerances, growth strategies, and resilience mechanisms, the entire structure becomes fragile. Starfish help prevent this fragility. They act as moderators, preventing any species from winning too easily. Their feeding creates openings for rare or slow-growing corals to settle. It maintains the shifting patchwork of species that gives reefs their resilience. In ecosystems that depend heavily on competition, the presence of a regulator is essential. Without it, natural selection becomes too intense, favoring a narrow subset of traits that may not withstand environmental change. Some starfish species exhibit remarkable patterns of movement across reefs. Studies using time-lapse imaging show starfish traveling along predictable routes, often returning to the same coral patches year after year. This suggests either long-term memory or a sensitivity to persistent chemical cues. They may be responding to growth rates, coral stress signals, or subtle changes in microbial communities. Whatever the mechanism, their movements are not random. They function like caretakers, visiting areas that require regulation while leaving others alone until needed. Even starfish larvae play a role in maintaining reef structure. Their planktonic forms drift through the water column, feeding on tiny particles and contributing to the transfer of nutrients between water layers. When they settle, their choice of habitat, influenced by currents, algae distribution, and chemical signals, helps determine which sections of reef will host future generations of regulators. The alliance that starfish forge with the reef is therefore not a partnership in the traditional sense. It is not built on mutual assistance or direct cooperation. Instead, it is a hidden contract between the ecosystem and its regulators. The reef produces the diversity of potential prey. The starfish consume selectively to maintain the mosaic of life. This feedback loop ensures that no single competitive strategy overwhelms the others. It ensures that the reef remains dynamic rather than stagnant, diverse rather than monotonous. When this balance collapses, when starfish outbreaks surge uncontrollably, or when starfish disappear due to environmental stress, the consequences are sweeping. Coral communities shift in composition, often becoming dominated by aggressive species. Structural complexity declines. The fish that depend on diverse coral formations lose their habitats. Feeding networks fragment. The reef begins a slow slide toward homogenization and vulnerability. Eventually, the collapse of complexity makes the entire ecosystem susceptible to bleaching events or disease outbreaks that it might otherwise have survived. Thus, the starfish, moving slowly across the reef with barely visible determination, becomes one of its most important architects, not by building, but by undoing, not by creating, but by clearing. Not through speed, but through persistence. Every meal a starfish consumes resets a tiny portion of the reef's competitive landscape. Taken together across years, these decisions carve the ecological identity of the entire system. In the end, the starfish is not a simple grazer or predator. It is a governor of growth, a stabilizer of diversity, and a quiet force shaping the future of the reef with every slow, deliberate step. Through patience and pressure, it ensures that the community remains rich, balanced, and adaptable, a living testament to the power of the smallest regulators in the largest ecosystems.